Hello and welcome to Sleepy Science. What if the world only feels normal because you never look closely enough? What if touching a table, seeing a star, standing in an empty room, or simply existing inside your own body is hiding rules so strange that reality almost feels impossible? In this journey, we'll uncover the hidden science beneath ordinary life, why you never truly touch anything, why solid objects are mostly empty space, why time changes under gravity, why space can stretch faster than light, why empty space is not truly empty, and why light, sound, water, magnets, and matter behave in ways that feel almost unreal. We'll also look inward, into a body built from ancient star-made atoms, glowing faintly, rebuilding itself, carrying DNA packed into microscopic space, and aging through many hidden processes at once. These are not myths or science fiction. They are real pieces of physics, biology, astronomy, and chemistry. Quiet truths that show reality is far stranger than it looks. So tap like, hit subscribe, and step into the hidden rules of reality with me. Because the closer we look, the more the ordinary world begins to feel impossible. You never truly touch anything. The next time your fingertips press against a table, pause for a moment and notice how completely real it feels. The firmness, the resistance, the quiet certainty that your skin has met something solid. It seems like the simplest truth in the world. Your hand is there, the table is there, they touch, but beneath that ordinary moment, nature is doing something much stranger. At the deepest level, what you call touch is not two solid things truly merging or making perfect contact. It is a conversation between forces. It is the outer electrons of the atoms in your skin being pushed back by the outer electrons of the atoms in the table, long before the tiny centers of those atoms ever come close to meeting. You do not feel the table because your matter passes into its matter. You feel it because the electromagnetic force says no. That no becomes pressure. Pressure becomes a nerve signal. The nerve signal travels through your body. Your brain receives it, interprets it, and turns invisible resistance into the feeling of contact. So the hard surface beneath your palm is not hard in the way your instincts imagine. It is not a wall made of perfectly packed little stones. It is mostly space, held together by fields, charges, and rules so reliable that your brain calls them solid. This does not mean touch is fake. It means touch is more mysterious than it appears. When you hold a cup, shake a hand, walk barefoot across the floor, or feel rain against your face, your body is reading patterns of force. The atoms in you and the atoms outside you are not blending like drops of water. They are approaching, resisting, adjusting, and sending information through the boundary between them. In everyday life, this boundary feels simple because it works so perfectly. A chair supports you, a door stops you, a pencil rests between your fingers. But if you could shrink down far enough to watch the atomic level, the scene would not look like tiny objects scraping against each other. It would look more like clouds of electric influence pressing back, deforming slightly, refusing to occupy the same arrangement. The reason your hand does not pass through the table is not because the table is completely filled with stuff. It is because the particles inside matter obey rules that prevent the atoms from collapsing into one another. Electrons carry electric charge and like charges repel. On top of that, there is a quantum rule that stops certain particles, like electrons, from all piling into the same exact state. Together, these effects help give matter its structure. They create the resistance you experience as solidity. In a quiet way, every touch is a tiny act of negotiation. Your skin pushes downward, the table pushes upward, and the balance between those forces becomes the sensation you trust. This is why the idea that you never truly touch anything should not be understood as a cheap illusion or a dramatic trick. It is not saying your world is imaginary. It is saying your world is built from interactions, not from the kind of direct contact your mind pictures. The feeling is real, the signal is real, the physics is real, but the story your senses tell you is simplified, like a smooth icon hiding an entire machine underneath. Your nervous system does not need to show you electron clouds, atomic spacing, or electromagnetic repulsion. It only needs to tell you, there is something here. It is firm. Do not move through it. That is enough for survival. That is enough to walk, grip, build, write, embrace, and live. But when you look closer, even the most intimate forms of contact become strangely distant. When you hold someone's hand, the warmth you feel comes from energy moving through tissues and nerve endings, but the atoms of your hand and theirs still keep their microscopic boundaries. When you lean against a wall, the wall is not simply there as one solid block. It is a structured storm of particles and fields maintaining order. When your feet touch the ground, what actually happens is a vast number of tiny electrical repulsions, coordinating so smoothly that you feel one continuous surface beneath you. The ground is pushing back against you, and your body translates that push into the feeling of being supported. That support is one of the quiet miracles of ordinary life. You are not falling through the floor because invisible forces are working at every point of contact, every second, without asking for your attention. And maybe this is where the science becomes more than science, because touch is one of the ways you confirm that you exist. You reach out and the world answers. A surface resists you. A hand squeezes yours. A blanket folds around your body. A drop of water lands on your skin. These experiences feel like proof that you are not alone inside your own mind. Yet the truth beneath them is even more delicate. Connection does not require complete merging. Contact does not require two things to lose their boundaries. In fact, the boundary is what makes the experience possible. If your atoms and the table's atoms simply blended without resistance, there would be no touch, no pressure, no shape, no separation between you and the world. Solidity comes from refusal. Feeling comes from resistance. The world becomes tangible because things do not fully collapse into one another. That is a strange and beautiful thought. The same force that keeps you apart from everything is also what allows you to feel anything at all. So when you press your hand against glass, or trace your fingers across wood, or rest your head on a pillow at night, you are experiencing a carefully translated message from the invisible architecture of matter. You are feeling the edge of the world without ever crossing fully into it. And perhaps that makes ordinary touch more meaningful, not less. Because every moment of contact is really a meeting at a boundary, a near encounter between fields, a silent exchange between your body and everything outside it. You never truly touch anything in the simple way you imagined as a child, but you are always interacting, always exchanging force, heat, motion, and information, always being answered by the universe in the language of pressure and sensation. And maybe that is enough. Maybe touch was never about absolute contact. Maybe it was always about response. The world pushes back, and your brain turns that push into certainty. Your hand reaches out and reality replies, "I am here." Solid objects are mostly empty space. A stone in your hand feels like the opposite of emptiness. Yet if you could open it the way you open a room and step inside its smallest architecture, you would find that matter is not packed the way your senses suggest. It is not a solid block all the way down. It is more like a vast organized emptiness with tiny centers of mass and energy arranged inside it so precisely that from your human scale, it becomes strength, weight, texture, and shape. Every object around you, the floor, your phone, your bones, the walls, the chair beneath you, is made of atoms. And atoms are strange little systems with a dense nucleus at the center and electrons spread around it in regions of possibility. The nucleus contains almost all the atom's mass, but it is incredibly small compared with the space the atom occupies. If an atom were enlarged until its nucleus became the size of a small seed placed in the middle of a stadium, the outer region where its electrons are found would stretch far away around it, leaving an enormous amount of space in between. That comparison is not exact in every detail, because atoms are not tiny solar systems, and electrons are not little planets orbiting in neat circles. But it gives you the feeling of the truth. Most of what you call solid matter is not solid in the everyday sense. It is structure, it is arrangement, it is energy held in stable patterns. And this is the first quiet shock of the topic. The world feels full, not because it is full like a box packed with sand, but because nature has built reliable rules that make emptiness behave like substance. When you place a book on a table, the book does not fall through because its atoms and the table's atoms are organized in ways that resist being pushed into the same physical arrangement. The table feels continuous because trillions upon trillions of atoms are locked into a pattern, especially in solid materials where atoms are held in place by bonds. These bonds are not little hooks or glue strings you could see with your eyes. They are relationships created by the behavior of electrons and forces between charged particles. In a crystal, atoms can line up in repeating patterns, giving the material a clear internal order. In metal, some electrons can move more freely, helping conduct electricity and heat. In glass, atoms are arranged more irregularly, which is why glass behaves differently from a crystal, even though both can feel hard. Solidity, then, is not one simple thing. It is a result of countless microscopic relationships working together. A diamond is hard because carbon atoms are bonded in a tight three-dimensional network. Rubber bends because its long molecules can stretch and shift. Wood has grain because it grew as living tissue, carrying layers and fibers from a tree's life. So when you say an object is solid, you are summarizing a hidden world of atomic architecture. You are touching the result, not seeing the cause. But there is an even deeper detail that makes the phrase mostly empty space more mysterious. The space inside atoms is not empty like a dead, silent void. It is not nothingness in the simple way we imagine a blank gap. It is filled with fields, probabilities, and the conditions that allow particles to exist and interact. Electrons do not sit like beads at fixed points unless measured in specific ways. They behave more like spread out patterns of possible location, described by quantum physics. This means the atom is not a tiny solid dot surrounded by a clean, empty shell. It is a subtle structure of presence and possibility. The emptiness inside matter is active. It has rules. It has tension. It has behavior. It is part of why atoms have size in the first place. If you removed all the space inside atoms and somehow compressed the actual dense material of a human body into only its most compact parts, the result would be unbelievably tiny, yet it would still carry the mass. This is why extreme cosmic objects like neutron stars are so astonishing. Under immense gravity, matter can be crushed into states far denser than anything on Earth, showing us that ordinary solidity is not the final form of matter, only the familiar form we live with. Your everyday world is spacious because the forces inside matter are allowed to hold atoms apart at stable distances. That spaciousness is not weakness. It is designed by natural law. It allows chemistry to happen. It allows molecules to form. It allows cells, rocks, oceans, bones, paper, air, and skin to exist in different ways. If everything were packed with no internal space, there would be no flexibility, no chemistry as you know it, no living systems carefully folding proteins, no water molecules moving and bonding, no lungs exchanging gases, no brain cells passing signals. The emptiness inside matter is not useless. It is the room in which structure becomes possible. This changes the way you look at the objects around you. A wall no longer seems like a simple barrier, but like an enormous agreement between atoms. A mountain becomes a frozen pattern of particles arranged through pressure, heat, time, and geology. Your own body becomes not a solid statue, but a temporary organization of atoms borrowed from food, water, air, and ancient stars, held together for a while in the shape of you. And yet, you do not experience yourself as mostly empty. You experience weight, warmth, heartbeat, hunger, breath. This is because your senses are not built to show you atomic reality. They are built to guide you through the human-scale world where objects are stable enough to matter. Your brain does not need to tell you that the chair is made of atomic spacing and force relationships. It only needs to tell you that the chair can hold you. That is the strange kindness of perception. It hides the complexity so you can live. But when you learn the truth, the ordinary world becomes deeper without becoming less real. The cup is still a cup. The floor is still a floor. Your body is still your body. The difference is that now you understand they are not solid in the blunt way they appear. They are patterns of matter held open from within, like music made of pauses as much as notes. A song would not exist if every sound were pressed together with no silence between them. In the same way, Matter would not have its familiar forms without the hidden spacing inside it. The world is built not only from what is there, but from the gaps that allow what is there to take shape. So the next time you look at a stone, a glass of water, a door, or your own hand, remember that solidity is not the absence of emptiness. It is emptiness organized so beautifully that it can carry weight. It can become shelter. It can become bone. It can become a planet beneath your feet. And maybe that is what makes reality feel so impossible when you finally notice it. The things that seem most solid are also full of hidden openness. And the world you trust every day is held together not by being completely filled, but by knowing exactly how much space to leave. Time runs differently, depending on gravity. A clock on the floor and a clock on the roof are not living in exactly the same time, even if they sit in the same house under the same sky, counting the same quiet seconds. That sounds impossible at first, because your life teaches you to treat time as one shared river, moving evenly for everyone and everything. Morning arrives for the whole city, night falls over every street. A minute on your phone feels like a minute in your body. But physics has shown us something deeper and far less intuitive. Time is not universal. It does not flow at one perfect speed everywhere. It bends, stretches, and slows depending on gravity. The stronger the gravity around you, the more slowly time passes compared with a place where gravity is weaker. This is not a metaphor. It is not science fiction. It is one of the real consequences of Einstein's general theory of relativity, and it has been measured with extremely precise clocks. Place one clock closer to Earth's surface, where gravity is slightly stronger, and another higher up, where gravity is slightly weaker, and over time they will not agree perfectly. The difference is tiny in ordinary life, too small for your senses to notice, but it is real. Time near sea level runs just a little slower than time on a mountain. Time near a massive planet would run slower than time far away in space. And near something as extreme as a black hole, the difference could become so dramatic that the universe outside might seem to race ahead while your own local time feels normal to you. This is the first thing to understand clearly. You would not feel your own time slowing down. Your heartbeat, your thoughts, your breathing, the blinking of your eyes, the movement of your hands, all of it would feel ordinary from your own point of view. Time always feels normal to the person inside it. The strange part only appears when two different places compare their clocks. Imagine two twins. One stays far from strong gravity, while the other spends time near an extremely massive object. When they meet again, they may not have aged by the same amount, not because one of them was frozen, and not because time stopped in a magical way, but because space-time itself is shaped by mass and gravity. In Einstein's picture, gravity is not simply a pulling force in the old everyday sense. Massive objects change the geometry of space-time, and clocks follow that geometry. A clock deeper in a gravitational field takes a slightly slower path through time than a clock farther away. It is as if the universe has no single master clock hidden behind reality. Instead, every clock belongs to its own location, its own motion, its own gravitational environment. The result is quiet but profound. The time you experience is local. It belongs to where you are. This matters not only in black hole thought experiments, but in technology you use every day. GPS satellites orbit high above Earth, where gravity is weaker than it is on the surface. Their clocks tick at a slightly different rate from clocks on the ground. At the same time, their motion also affects their timing, because movement through space changes time as well. Engineers must correct for these relativistic effects, or GPS navigation would slowly become inaccurate. Your phone finding your location on a map depends on the fact that time is not the same everywhere. That is one of the most beautiful details in modern science. A discovery that sounds cosmic and abstract is quietly working inside ordinary directions, deliveries, flights, and walks through a city. The universe does not ask whether a fact feels intuitive before it becomes useful. It simply behaves the way it behaves, and we learn to adjust our machines around the truth. Even on Earth, the effect of gravity on time can be measured with atomic clocks so precise that scientists can detect tiny differences in height. A clock raised upward by a small amount can tick at a slightly different rate than one lower down. The difference is unbelievably small, but the meaning is enormous. It tells us that time is not merely something we imagine. It is woven into the physical structure of the world. It responds to gravity like a fabric responding to weight. Not visually, not dramatically in daily life, but with mathematical patience. The deeper you go into a gravitational field, the slower your clock runs compared with clocks farther away. This is why black holes become the most haunting example. A black hole is not a vacuum cleaner in space, but a region where gravity is so intense that beyond a certain boundary, light itself cannot escape. If you watch someone fall toward that boundary from far away, their signals would seem to slow and fade. Their clock, from your distant perspective, would appear to tick more and more slowly, but from their own perspective, time would continue forward normally as they crossed, assuming the black hole was large enough that the crossing itself was not immediately destructive. This is where the human mind begins to strain, because the same event can have different descriptions depending on where you are. There is no simple, universal now that everyone in the universe must agree on. Your present is not a cosmic command. It is a local experience. Somewhere far above you, time is passing at a slightly different rate. Somewhere deep in the gravity of a star, time is slower still. Somewhere near a black hole, the difference can become almost unbearable to imagine. And yet nothing feels strange from within each place. Every observer carries their own normality. Every clock believes it is honest. This can make reality feel less like a rigid stage and more like a layered composition, where each location plays its own tempo while still belonging to the same cosmic music. The lesson is not that time is fake. It is that time is more physical than we once thought. It is affected by the shape of the universe, by mass, by gravity, by where you stand. The seconds you feel are real, but they are not absolute. They are part of a relationship between you and space-time. And maybe that is what makes this truth so quietly humbling. You are not moving through a perfect, invisible river that flows the same for all things. You are living inside a universe where even time has weather, where gravity can deepen the rhythm of existence, where a mountain and a valley do not quite agree on how fast the future arrives. So the next time you look at a clock, do not think of it as measuring something simple. Think of it as listening to the local heartbeat of reality. Think of every second as faithful, but not universal. And somewhere, high above you, or deep beside a massive star, another clock is telling the truth too, just a slightly different one. The universe has no known center. If you could rise above Earth, above the sun, above the Milky Way, and keep pulling farther back until galaxies became faint dust scattered across darkness, you might expect to eventually find the middle of it all. Some sacred point where the universe began. Some hidden throne from which everything spreads outward. But the strange truth is that modern cosmology gives us no such center. The universe, as far as we can tell, has no known central point. Not Earth, not the sun, not our galaxy, not even some distant region beyond our telescopes has been identified as the place from which everything is expanding. This feels wrong at first because your brain is trained by ordinary objects. A room has a middle, a circle has a center. An explosion has a place where it started. A ripple in a pond spreads from a point. So when you hear that the universe is expanding, your imagination naturally pictures galaxies flying away from one original location, like sparks from a firework. But the real picture is more subtle and much more unsettling. The universe is not expanding from a center inside space. The distances between faraway galaxies are growing because space itself is changing on the largest scales. This means that no matter where you stand in the cosmos, if you could look far enough, you would see distant galaxies moving away from you in every direction. From our position, it looks as if we are near the center, but an observer in a galaxy billions of light years away would see the same kind of pattern from their own location. They would also appear to be surrounded by a universe stretching away in all directions. This is not because every place is secretly the one true center. It is because the expansion has no preferred middle within the universe that we can observe. Every location can look central from its own point of view, the same way every person standing in an open fog can feel like the fog surrounds them equally. The mistake is thinking that centered on me means center of everything. In astronomy, this difference matters deeply. We live at the center of our observable universe, but not because we are special. We are at its center for the same reason you are always at the center of how far you can see. Your horizon follows you. If you stand in a field, the visible landscape seems to circle around you, but that does not mean the field was made for you. The observable universe is like that on a cosmic scale. It is the region whose light has had enough time to reach us since the early universe became transparent. Beyond that limit, there may be much more universe, perhaps enormously more, but its light has not reached us, and may never reach us depending on how space continues to change. So when scientists say the universe has no known center, they are not saying we have searched every possible place and found nothing marked with a cosmic flag. They are saying the evidence we have points to a universe that, on very large scales, looks broadly similar in every direction and does not reveal a preferred central location. The cosmic microwave background, the ancient afterglow of the early universe, reaches us from all directions with remarkable smoothness, with only tiny variations that later helped seed galaxies and clusters. Those small differences matter, but they do not point to a single cosmic middle. Large galaxy surveys also show a universe that becomes more evenly distributed when viewed across enormous distances, even though smaller regions contain clusters, filaments, voids, and beautiful unevenness. This large-scale sameness is one of the reasons cosmologists use the idea that no location should be treated as privileged unless evidence forces us to. It is a humbling principle. The universe does not appear to place us in a special seat. For centuries, humans were tempted to imagine themselves near the middle of creation. Then we learned Earth orbits the Sun. Then we learned the Sun is one ordinary star among hundreds of billions in the Milky Way. Then we learned the Milky Way is one galaxy among vast numbers of galaxies. And now even the idea of a universal center slips away. Not because we have become less meaningful, but because reality is larger and less human-shaped than our instincts want it to be. There is a quiet freedom in that. If there is no known center, then the universe is not arranged like a stage with one spotlight. It is more like a vast relational structure, where position only makes sense compared with other things. Up and down depend on gravity nearby. Left and right depend on your body. Center and edge depend on the shape of what you are describing, but the whole universe may not offer those familiar handles. It may be infinite, in which case every attempt to find a middle becomes meaningless, because an infinite thing has no central point in the ordinary sense. Or it may be finite, but curved in a way that has no boundary you could travel to. Just as the surface of Earth has no edge even though it has a limited area. That does not mean the universe is exactly like Earth's surface. It only gives your mind a gentler doorway into the idea that something can be complete without having a center inside itself. And this is where the science begins to touch something quietly philosophical. You are used to locating yourself by reference points. Your home, your country, your planet, your star. But on the deepest cosmic scale, location loses its emotional certainty. You are not central, but you are not off-center either. You are not at the edge because no edge is known. You are not in a forgotten corner because corner may not apply. You are simply here, inside a universe where every observer builds a visible bubble around themselves, mistaking perspective for placement until science teaches them to see more carefully. That lesson reaches beyond astronomy. So much of human thought begins with the feeling that our viewpoint must be the natural one. We look from where we are and quietly assume reality is arranged around that angle. But the universe teaches a softer discipline. What surrounds you is not always centered on you. What feels obvious may be a consequence of where you happen to stand. The night sky is not a ceiling above a central world. It is a depth without a known middle, filled with other possible observers, each carrying their own horizon, each able to believe for a moment that everything recedes from them. And maybe that is what makes this truth so powerful. The The universe has no known center, yet every conscious place becomes a center of experience. Not a physical center, not a throne, but a point from which reality is witnessed. You are not the middle of the cosmos, and still the cosmos becomes visible through you. You are not the reason galaxies move, and still you can understand their motion. You are not placed at the heart of everything, and still your small life participates in the only thing that makes center meaningful at all. Awareness, perspective, and the courage to look outward without needing the universe to revolve around you. Space can expand faster than light. A beam of light is the fastest messenger inside the universe, yet the universe itself can widen the distance between places so quickly that even light begins to lose the race. That sentence feels like a contradiction because we are often taught one simple rule: nothing can travel faster than light. And that rule is real, but it has a hidden condition. It applies to things moving through space. A rocket, a particle, a signal, a flash of light passing from one place to another. It does not place the same kind of limit on the stretching of space itself. This is where the ordinary imagination begins to break, because we naturally picture space as an empty stage where objects perform their motions. A galaxy moves this way, a planet moves that way, a photon crosses the darkness like an arrow. But in modern cosmology, space is not merely a stage. It is part of the system. It can change, it can stretch, it can increase the distance between galaxies, even when those galaxies are not racing through space like objects with engines. On very large scales, distant galaxies can appear to recede from us faster than light, not because they are locally breaking the cosmic speed limit, but because the space between us and them is expanding. Think of dots drawn on a surface that is slowly being stretched. Each dot may sit calmly in its local region, yet the distance between far apart dots grows as the surface expands. The farther apart the dots are, the more stretching lies between them, so the faster their separation increases. The same basic idea applies to the universe, though the real universe is not a simple surface, and the details are deeper. Nearby galaxies can move toward or away from us because of local gravity, but at enormous distances, the expansion of space dominates. The more space there is between two distant regions, the more space there is to stretch. This is why a galaxy far enough away can have its distance from us increasing faster than light, without any ship, star, or atom in that galaxy flying through its own nearby space faster than light. Locally, physics remains obedient. Light still moves at light speed through its own neighborhood. Relativity is not broken, the rule is protected. What changes is the distance that light must cross, while the road itself is lengthening. Imagine walking along a moving walkway that keeps extending in front of you. You may be walking as fast as you are allowed, but if the walkway grows faster than you can cover it, your destination still gets farther away. A photon from a very distant galaxy can travel faithfully at light speed, second after second, year after year. And yet the space between that photon and us may keep stretching so much that the photon makes little progress toward reaching us. In some cases, it may never arrive. This is one of the quietest and most haunting truths in cosmology. There are regions of the universe whose light will never reach us, not because the light is weak or because the stars are hidden behind dust, but because expansion carries those regions beyond any possible future contact. The universe does not need walls to separate places forever. It only needs space to keep growing. This is also why faster than light in cosmology should not be imagined as a galaxy speeding past a cosmic police officer. It is not a violation in the usual sense. It is a sign that the universe is not built to satisfy the small-scale intuitions we develop on Earth. Here, distances are modest. Rooms do not expand while you cross them. The space between your hand and a cup does not stretch faster than your motion. Roads do not become longer because reality itself is swelling. So your brain builds a practical model. Speed means motion through a fixed background. But on cosmic scales, that model is incomplete. The background is dynamic. The distance itself can evolve. Scientists describe this expansion by looking at how light from faraway galaxies is stretched as it travels. When space expands, the wavelengths of light stretch too, shifting the light toward redder colors. The farther a galaxy is, in general, the more its light has been stretched by cosmic expansion. This redshift is one of the great clues that the universe is not still. It carries the history of expansion inside the light itself, like a message written not in words, but in the lengthening of waves. And if you follow that clue backward, you arrive at an early universe that was much hotter, denser, and more compressed than it is now. In one especially important early phase called inflation, space is thought to have expanded incredibly rapidly, taking tiny regions and stretching them to enormous size in a fraction of a moment. Inflation is not just an exotic idea added for drama. It helps explain why the universe looks so smooth across vast distances, and why tiny early variations could later grow into galaxies and clusters. It suggests that the universe's largest structures may have their roots in microscopic fluctuations stretched across cosmic scales. The strange thing is that this expansion did not throw matter through space faster than light like shrapnel. It enlarged space itself. That distinction matters. Without it, the idea sounds impossible. With it, the impossible becomes one of the foundations of modern cosmology. And yet, even when you understand the explanation, there is still something emotionally difficult about it. Space expanding faster than light means the universe is not fully reachable. It means there are places that may exist, with galaxies and stars and perhaps worlds of their own, that are permanently outside our ability to see or influence. Not because we lack better telescopes, not because we are too early in history, but because reality has horizons built into it. There is a limit to what light can bring us, a limit to what information can cross, a limit to how much of existence can ever become part of our story. The night sky may look like an invitation, but it is also a boundary. Every telescope is a way of listening, and some parts of the universe are already too far for their voices to ever arrive. This does not make the cosmos less beautiful. It makes it more profound. It means the universe is not a small container waiting to be fully mapped, but a living geometry of distance and time, opening faster in some directions than knowledge can follow. And maybe this is why the idea stays with you. Light is the symbol of seeing, knowing, reaching, understanding. But space can expand faster than light, which means there are truths that may be real without ever becoming visible to us. There are regions that may be present in the full universe, but absent from our experience forever. Human beings often confuse reality with accessibility. We imagine that if something exists, then with enough effort, enough technology, enough patience, we should eventually be able to touch it, measure it, or receive its signal. Cosmology gently refuses that hope. It says some doors are not locked. They are simply carried away by the growth of space itself. Still, there is a strange comfort in knowing the rule. The universe is not chaotic in this. It is not cheating. It is following a deeper order than the one our senses expected. Light remains the fastest traveler through space, but space is not a traveler. It is the distance being born between travelers. So the next time you look upward and imagine light crossing the darkness, remember that the darkness is not just sitting there. On the larger scales, it is stretching, carrying some galaxies beyond the reach of every future eye. And somewhere, far beyond what we may ever see, the universe may continue unfolding, not against the speed of light, but around it, quietly reminding us that even the fastest thing in nature cannot outrun the growth of the stage on which nature appears. Most of the universe is missing from what we can see. The night sky looks full only because your eyes are easily impressed by the few things bright enough to announce themselves. Stars shine, galaxies glow, nebulae spread like painted smoke across deep space. Through telescopes, the universe seems crowded with light, structure, and motion, as if the darkness is only the background behind everything real. But modern science has discovered something far more disturbing and far more beautiful. Almost everything shaping the universe is not something we can see directly. The glowing matter we admire, Stars, planets, gas clouds, dust, galaxies, and the ordinary atoms that make your body is only a small fraction of what appears to exist. Most of the universe is missing from vision. Not missing as in gone, not missing as in imaginary, but missing from the simple human habit of believing that reality must shine to be real. The universe is dominated by things that do not glow like stars, do not reflect light like planets, and do not reveal themselves in the ordinary way our senses understand. We know they are there because they leave fingerprints. They bend light. They pull on galaxies. They shape the growth of cosmic structure. They influence the fate of space itself. And yet when we try to look straight at them, we find no face, no color, no surface, no familiar substance waiting in the dark. This is where the story begins to deepen. Astronomy is not only the science of what can be seen, but the art of discovering what must be there because the visible universe behaves as if it is being guided by invisible hands. One of those hidden ingredients is called dark matter. The name sounds dramatic, but it is really a confession of ignorance. Dark does not mean evil or shadowy in a mystical sense. It means it does not interact with light in the normal way. It does not shine. It does not absorb light clearly, and it does not scatter light in a way that lets our telescopes easily catch it. But its gravity seems to be everywhere. When astronomers studied how galaxies rotate, they found something strange. Stars far from the centers of galaxies were moving too quickly for the visible matter alone to hold them in place. If only the stars and gas we see were creating the gravity, many galaxies should not behave the way they do. Their outer regions should move differently. Some structures might not hold together. Something unseen appears to be adding gravitational mass, like an invisible framework around and through galaxies. Dark matter is not just an extra detail added to make equations tidy. It helps explain why galaxies spin the way they do, why galaxy clusters hold together, why light from distant galaxies can be bent by mass we cannot see, and why the early universe developed into the web-like structure we observe today. Gravitational lensing is one of the clearest clues. When light from a faraway galaxy passes near a massive cluster, its path can bend, creating distorted arcs or multiple images. Sometimes the amount of bending tells us there is more mass present than the visible galaxies and hot gas can explain. It is as if the universe is drawing a map of hidden gravity using light as the ink. One especially powerful clue comes from galaxy cluster collisions, where visible hot gas and the strongest gravitational influence appear separated, suggesting that much of the mass passed through in a form that did not behave like ordinary gas. This does not mean scientists know exactly what dark matter is. They do not. It may be made of particles we have not yet detected directly. It may require new ideas beyond the physics we currently use. Some researchers explore alternative explanations involving gravity itself. But the dark matter picture remains powerful because it fits many different observations at once. Still, the mystery is open. Underground detectors, particle experiments, and astronomical surveys continue to search, and so far, no dark matter particle has been confirmed in the way a simple story would like. That silence is not failure. It is information. It tells us the hidden universe is not easy to catch. But dark matter is only part of the missing story. There is an even larger and stranger ingredient called dark energy, a name given to whatever is causing the expansion of the universe to accelerate. In the late 20th century, observations of distant exploding stars showed that the universe's expansion was not slowing down as many expected from gravity. Instead, on the largest scales, it seemed to be speeding up. Something appears to be built into space itself, or connected to space in a way we do not yet fully understand, pushing the cosmic expansion forward. Dark energy is not a substance you can hold, not a wind blowing through galaxies, not an engine hidden at the edge of space. It is a placeholder for a deep unknown. It may be related to the energy of empty space. It may be something more dynamic. It may reveal that our understanding of gravity on cosmic scales is incomplete. The honest answer is that science has a strong description of what dark energy seems to do, but not a complete explanation of what it truly is. And this honesty is what makes the subject powerful. The universe is not less scientific because it contains mystery. It is more scientific because we can name the limits of what we know and build careful questions around them. When you add the picture together, ordinary matter, the kind made of atoms, the kind that becomes stars, oceans, skin, bones and breath, is only the visible minority of the cosmic budget. Dark matter and dark energy dominate the story, yet neither one is directly visible to human eyes. This should change the way you think about seeing. Sight is only one doorway. Light is only one messenger. Reality is not required to be bright in order to be real. A thing can be unseen and still shape the motion of galaxies. It can leave no color and still bend the path of light. It can resist every attempt at direct detection and still be necessary for the universe we observe to make sense. In your daily life, you are used to trusting surfaces. You believe the visible is the important part. The face, the flame, the skyline, the star. But cosmology teaches a quieter discipline. The visible may be only the decoration on a much deeper structure. The glowing universe is like foam on a dark ocean, beautiful and real, but not the whole sea. Every galaxy you see in a telescope may be embedded in a larger halo of unseen matter. Every cluster may sit inside a gravitational architecture made mostly of what does not shine. And the future of all those galaxies may be governed by an unknown component that stretches the cosmic story toward colder, wider, more isolated ages. This is not fantasy. It is the current frontier of evidence and uncertainty. The humbling part is that humans built telescopes to gather light and found out that light was not enough. We mapped the bright universe and discovered the bright universe was not the full universe. We looked outward expecting to collect answers, and instead found that most of existence does not introduce itself directly. Maybe that is the lesson hidden inside the darkness. Knowledge does not begin when something becomes obvious. It begins when the obvious stops being enough. The stars are not lying to you, but they are incomplete. The galaxies are not illusions, but they are not alone. The darkness between them is not empty scenery. It may contain the main structure of the cosmic story. So the next time you look at the night sky, let the stars impress you, but do not let them fool you. What shines is only the visible sentence. What holds the sentence together may be written in invisible grammar. And somewhere beyond the reach of ordinary sight, most of the universe is quietly doing its work, unseen, unnamed, and yet powerful enough to shape everything you have ever called real. The Big Bang did not explode into empty space. The Big Bang was not a bomb going off in a dark room because there was no room waiting for it. That is the first idea that must be gently removed from the mind, because almost everyone imagines the beginning of the universe as an explosion, a tiny point suddenly bursting outward, throwing matter into empty space like sparks from fire. It is a powerful image, but it is not what the science says. The Big Bang was not matter exploding into a pre-existing emptiness. It was the rapid expansion and cooling of space itself from an earlier state that was unimaginably hot, dense, and compact. The difference matters because an explosion happens somewhere. It has an outside. It has a surrounding space for debris to fly into. But the Big Bang was not an event inside the universe. It was an event involving the universe. The early universe was not a little fireball sitting in darkness. It was everything that would become the visible cosmos, and perhaps far more than what we can ever observe. In a state where distance, temperature, matter, and radiation were all bound together in a way the human imagination struggles to hold. If you could rewind cosmic history, galaxies would not simply fly backward through a fixed empty background until they met at one central point. Instead, the distances between all unbound regions would shrink. The universe would become hotter, denser, brighter, and more uniform. Not because all objects were rushing to one location, but because the scale of space itself was smaller. Every region was closer to every other region. Every future galaxy, every future star, every atom that would later become stone, ocean, air, skin, and thought belonged to an early cosmic condition where the universe was filled with searing energy. This is why the Big Bang is better understood not as an explosion of matter, but as the beginning of the universe's expansion from a hot, dense phase. And even that word beginning must be handled carefully. Scientists can describe the universe back to extremely early moments with powerful evidence, but the absolute first instant remains uncertain. Our current physics becomes incomplete when pushed too far backward into conditions where gravity, quantum behavior, energy, and space-time may have been united in ways we do not yet fully understand. So the Big Bang is not a simple answer that closes the mystery. It is the doorway into the mystery, supported by evidence but still surrounded by questions. One of the strongest pieces of evidence is the cosmic microwave background, a faint ancient light that fills the universe from every direction. It is not light from stars. It is a cooled remnant from a time when the universe was young, hot, and filled with a glowing plasma, a state where light could not travel freely because it kept scattering off charged particles. For hundreds of thousands of years, the universe was not transparent. It was more like a luminous fog. Then, as space expanded and cooled, electrons and nuclei combined into neutral atoms, allowing light to move freely for the first time. That released light has been traveling ever since, stretched and cooled by cosmic expansion, until today we detect it as microwave radiation, an afterglow so faint and old that it feels almost like the universe remembering its own childhood. This glow tells us the early universe was once hot and dense everywhere we can observe, not that a fireball exploded from one spot. Another major clue comes from the abundance of light elements, especially hydrogen, helium, and small amounts of lithium. In the first few minutes, the universe was hot enough for simple atomic nuclei to form in a process called Big Bang nucleosynthesis. The predicted amounts of these early elements match observations remarkably well, giving us another reason to trust the broad story. The universe cooled in stages. First, it was too hot for atoms. Then atoms formed. Much later, gravity gathered matter into the first stars and galaxies. The deep structure you see in the universe today did not appear all at once. It grew from tiny early differences, small variations in density that gravity gradually amplified over billions of years. This is important because it replaces the explosive image with something more elegant. The universe did not begin as chaos flying into emptiness, then accidentally arrange itself. It began, as far as our evidence reaches, in a state that was hot, dense, and surprisingly smooth, with tiny imperfections that later became the seeds of everything large and luminous. Galaxies are not shrapnel from a cosmic blast. They are growths from early conditions shaped by gravity, cooling gas, dark matter, and time. Stars are not burning fragments of the explosion. They are later furnaces born when matter collected and collapsed under gravity. Planets are not leftover sparks. They are second-generation worlds, made from elements forged inside stars and spread by stellar deaths. Even your body belongs to a long chain of cosmic development that began with simple early ingredients and became richer only after stars lived and died. That is why the Big Bang is not just a story about the past. It is the first chapter in the history of complexity. It explains why the universe has a thermal memory, why galaxies are receding in patterns that point back to a smaller, hotter past, why the oldest light arrives from all directions, and why the simplest elements appear in the proportions they do. But it does not say there was empty space outside the beginning, waiting like a silent container. Asking what the Big Bang expanded into may be like asking what is north of the North Pole. The question uses a familiar direction in a place where that direction may no longer apply. Our language is built from rooms, objects, edges, and distances, so we keep trying to place the universe inside something larger, but the universe is not an object you can step outside of and watch from a distance. There is no confirmed external balcony from which the Big Bang can be viewed. There is only the universe itself, carrying its history in its light, its elements, its expansion, and its structure. And this is where the idea becomes quietly unsettling. If the Big Bang did not happen in space, but involved the early state of space itself, then the origin of the universe is not a location. It is not a place you could point to. It is a condition from which all places we can know evolved. The beginning is not far away. In a strange sense, every direction you look is looking back toward it, because the early universe was not over there, it was everywhere. The atoms in your room, the air entering your lungs, the ground beneath you, the distant galaxies beyond sight, all trace their story back to that hot, dense past. Not to a firework in the void, but to a time when the entire observable universe was young, compressed, and filled with radiation. So the real Big Bang is less like an explosion and more like the unfolding of a cosmic fabric whose earliest threads are still glowing faintly around us. It does not reduce the mystery, it deepens it. It asks you to imagine a beginning without an outside, expansion without a surrounding emptiness, history without a central blast point, and reality emerging not as debris thrown into darkness, but as space and time themselves entering the story. And perhaps that is why the truth is more powerful than the myth. A simple explosion is easy to picture and easy to forget, but a universe that did not explode into empty space. A universe whose beginning was everywhere, whose ancient heat still whispers through the sky, whose first minutes shaped the ingredients of stars and bodies. That kind of beginning stays with you. It turns the darkness above you into evidence. It turns every atom into a survivor of cosmic history. It turns the word beginning into something larger than a moment, larger than a place, and far stranger than the human mind first expected. Some stars you see may already be dead. Some of the lights above you may be memories wearing the shape of stars. When you look up at the night sky, it feels immediate, as if the stars are shining right now, in the same present moment you are breathing in. A bright point appears, your eye receives it, and your mind says, "There it is." But the sky is not a live picture. It is a delayed message. Every star you see is separated from you by distance so large that even light, the fastest thing that can travel through space, needs time to cross it. The sun is about 8 light minutes away, so the sunlight on your face left the sun around 8 minutes before you felt it. If the sun somehow vanished this instant, Earth would not know for about 8 minutes, because information itself cannot arrive instantly. That small delay is already strange, but the stars stretch the idea into something deeper. A star 10 light years away is seen as it was 10 years ago. A star 500 light years away is seen as it was 500 years ago. A star 10,000 light years away is not being seen in your present, but in a past older than written history. The night sky is not one moment. It is many moments layered together, each point of light arriving from a different year, century, or age. You are not only looking across space, you are looking backward through time, and the farther the source, the older the light. This is why the phrase, "some stars you see may already be dead," is both fascinating and easy to misunderstand. It does not mean every star in the sky is secretly gone. Most stars visible to the naked eye are within a few hundred or a few thousand light years, and many of them live for millions, billions, or even trillions of years, depending on their mass. Small red dwarf stars can burn so slowly that none in the universe have had enough time to die yet, because the universe is not old enough. Sun-like stars live for billions of years, so for many ordinary stars, the chance that they die during the short time their light traveled to Earth is low. But the most massive stars are different. They live fast. They burn their fuel intensely. Some survive only a few million years before ending in supernova explosions or collapsing into compact remnants. If a very massive star is thousands of light years away, it is possible that the light reaching your eye shows it as it was before its final death, while in its own local present, it has already changed forever. You would not know until the light from that final event arrived. The universe does not update itself instantly for us. It sends news at the speed of light, and until the news arrives, the old version remains visible. This means the sky can contain ghosts, not in a supernatural sense, but in the honest physical sense of delayed information. A star can remain in your sky after it has already ended where it is, because you are receiving its past. And when a star dies, it does not simply switch off like a lamp. The death depends on what kind of star it is. A star like the sun will not explode as a supernova. In the far future, it will expand into a red giant, shed outer layers, and leave behind a white dwarf, a hot, dense remnant that slowly cools over immense times. More massive stars can end violently, blasting heavy elements into space, leaving behind neutron stars or black holes. These deaths are not only endings, they are also makers. Many of the elements needed for rocky planets, oceans, and living bodies are forged or spread through stellar processes and stellar deaths. So when you look at a star that may already be gone, you are not only seeing loss, you are seeing part of the cycle that makes complexity possible. The death of stars enriches space. It gives later generations of stars and planets the ingredients that the first stars did not have in abundance. Iron, calcium, oxygen, silicon, and many other elements in the world around you are tied to cosmic histories far older than Earth. But the key idea here is not simply that stars die. It is that seeing is not the same as knowing the present. Your eye is always receiving old information from the cosmos. Even the moon is a little over 1 light second away, so you never see it exactly as it is right now. Mars may be minutes away by light, nearby stars are years away. Distant stars in our galaxy may be thousands of years away. And when telescopes observe galaxies millions or billions of light years away, they are looking at entire cities of stars as they were when Earth was younger. Sometimes before animals, before complex life, or before the sun itself even existed, depending on the distance. A galaxy in a deep image may look graceful and complete, but the light left it so long ago that its stars, gas clouds, and structure may have changed enormously by now. Some of its massive stars are certainly gone. Some new stars have formed. Some explosions have happened. Some worlds, if they existed, have lived entire histories whose light has not yet crossed the dark between us. The universe you see is therefore not the universe as it currently is everywhere. It is the universe as it has been allowed to reach you. That truth changes the emotional weight of the sky. A star is not just a point. It is a message with a travel time. It is an ancient event arriving quietly at your retina. The darkness between you and it is not empty delay. It is the reason the past can still appear present. In daily life, distance feels like separation. But in astronomy, distance also becomes memory. The farther you look, the deeper the memory becomes. And there is something humbling in realizing that your sense of now is local. The star has its own now, far away, but you cannot access it directly. You can only receive what left long ago. The sky teaches you that reality is not delivered all at once. It arrives in layers. You live in one moment, but you are surrounded by signals from many others. This is why astronomy is a kind of time archaeology. A telescope does not only enlarge objects, it collects older and older light. It lets us study stars at different stages of life. Nebulae where stars are forming, supernova remnants where stars have died, and ancient galaxies from the young universe. We cannot travel backward in time, but the universe has already done part of the work by sending old light toward us. Every clear night, the past is falling into your eyes. Still, honesty matters. Not every visible star is already dead, and most of the familiar bright stars are probably still shining in their own present, if they are not extremely massive and near the end of their lives. The wonder is not in exaggerating the truth. The wonder is that the real truth is already strange enough. Some stars may be gone. Some are changing. Some are younger in your sky than they are in themselves. Some light began traveling before the cities you know were built, before languages changed, before generations rose and disappeared. And yet it arrives gently, without announcing its age. It becomes a small white point above your roof, and your brain turns it into something simple, a star. But beneath that simplicity is a question that can stay with you long after the sky is gone from view. How much of what you call the present is only the past finally reaching you? The stars do not lie. They simply speak slowly because space is vast and light, though fast is not infinite. So the next time you look upward and see a silent bright point, remember that you may not be seeing a living flame exactly as it is. You may be seeing a message sent before you were born, before your ancestors were born, before whole human stories began and ended. And somewhere far away, the star itself may have changed beyond recognition, while its earlier light continues crossing the darkness, arriving here as beauty. That is the quiet ache of the night sky. It is alive with delayed truth, filled with ancient signals, and sometimes shining with the last visible memory of things that may no longer be there. Black holes can slow time almost to a stop. A black hole does not simply swallow light, it changes the meaning of waiting. Imagine watching a clock fall toward the darkest boundary in nature, a place where gravity has become so intense that escape is no longer a matter of power, speed, or courage, but of geometry itself. From far away, that clock would begin to behave in a way that feels almost supernatural. Its ticking would appear to slow. The light coming from it would stretch toward deeper and deeper red. Its movements would seem to fade, weaken, and freeze near the edge, as if time itself were being drained from the scene. This is the strange truth behind the idea that black holes can slow time almost to a stop. But the most important word is almost, and the most important question is, for whom? Because near a black hole, time does not stop in the simple way a movie pauses on a screen. A person falling in would not feel their own heartbeat freezing. Their thoughts would not stretch into eternity from their own point of view. If the black hole were large enough, and if they crossed the boundary without being torn apart first, they could pass the event horizon in a finite amount of their own time. The drama belongs mostly to the distant observer. Someone watching safely from far away would see the falling object's signals grow slower and dimmer, not because the object becomes physically frozen in its own experience, but because light climbing out of the black hole's gravity loses energy and takes longer, in a relational sense, to communicate what is happening. The closer the object gets to the event horizon, the more extreme this difference becomes. The event horizon is not a solid surface. It is not a wall, not a shell, not a glowing membrane you crash into like glass. It is a boundary in space-time. Cross it, and every future path that light or matter can take leads inward. Outside it, escape is possible with enough speed. Inside it, escape is no longer part of the future. That is why the horizon is so haunting. It is not dangerous because it burns like fire. It is dangerous because it changes which futures are available. And time, near that boundary, becomes part of the same strange structure. In ordinary life, you imagine time as a private rhythm inside your body. But around a black hole, the rhythm of your clock compared with a faraway clock can become wildly different. The deeper you are in the gravitational well, the slower your time appears from far away. A minute near the edge of a black hole could correspond to much more time for someone far outside, depending on the black hole's mass and how close you are to the horizon. This is not fantasy created for dramatic films. It is a real prediction of relativity, and it affects how light, clocks, and motion behave around extremely compact mass. But it must be understood carefully. You cannot hover exactly at the event horizon of a non-rotating black hole with an ordinary rocket, because remaining fixed, there would require impossible acceleration. The closer you try to hold position just above the horizon, the more violently you must fight gravity. Falling freely is different. To a falling observer, the horizon may not announce itself with a local sign at the exact crossing, especially for a supermassive black hole, where the tidal stretching at the horizon can be gentle. But for a small black hole, the difference in gravity between your head and feet could become lethal long before or near crossing stretching matter in a process often called spaghettification. That word sounds almost comic, but the reality is brutal. Gravity would pull harder on the closer part of your body than the farther part, creating tides strong enough to tear things apart. Yet supermassive black holes, the giants found in the centers of galaxies, can be so large that the horizon itself is crossed without that immediate shredding. The danger comes later, deeper inward, as all paths lead toward the central region where our current theories predict extreme conditions. This is where black holes force us to separate appearance from experience. From outside, the falling traveler seems to slow toward stillness. From inside their own falling frame, they keep moving forward. Both descriptions are part of the same reality, seen from different positions. The universe does not offer one simple master view that everyone must share. Around a black hole, perspective becomes physical. The light you receive, the clock you compare, the path you can take, all depend on where you are. Even the color of light tells the story. As light escapes from strong gravity, it becomes stretched, shifted toward redder wavelengths, then beyond visible red, into infrared, radio, and finally too faint to detect. A falling object does not remain visibly frozen forever, like a perfect statue at the horizon. In practice, it fades away. The image dims, the signal weakens, information becomes harder and harder to receive. The stopping is not a crisp photograph locked in the sky. It is a fading delay, a vanishing message, a final whisper stretched thinner by gravity. And black holes do not only distort the clocks of falling objects, they also shape the environment around them in fierce and luminous ways. Matter spiraling around a black hole can form an accretion disk, heating to extreme temperatures as friction, compression, and magnetic turbulence turn gravitational energy into radiation. Some black holes power jets that launch material across enormous distances, not from inside the horizon, but from the violent regions around it. This is why the darkest objects in the universe can sit inside some of the brightest neighborhoods. The black hole itself gives no light from within the horizon, but the matter struggling around it can shine with extraordinary intensity. Time dilation becomes part of that landscape too. Signals from the innermost regions can be stretched and warped. Orbits close to the black hole behave in ways no planet around the sun would. There are places where stable circular motion becomes impossible, where matter either escapes outward or plunges inward. Space and time are not passive background there. They are the terrain. The black hole is less like a monster inside space, and more like a wound in the rules of distance and duration, a place where the geometry of reality has been pulled into an extreme shape. Yet the real lesson is not that black holes are magic. The lesson is that time is not immune to the universe. It is not a separate, invisible metronome ticking above all things. It belongs to the fabric of reality, and black holes reveal that fabric under pressure. They show us that a second is not simply a second in all circumstances. They show us that watching and experiencing can disagree without either being a lie. They show us that the present is not delivered equally across every region of existence. Near a black hole, the future outside can rush ahead while your own clock insists nothing unusual is happening. That thought carries a quiet emotional weight. Somewhere in the universe, near the edge of an enormous black hole, a process could unfold in what feels like a short span locally, while distant stars age far more. A signal sent from near the horizon could arrive weakened, reddened, delayed, as if reality itself had difficulty letting the message go. And if you imagine a person there, even only as a thought experiment, you begin to feel the loneliness of relativity. The same event split into different truths, the same fall seen as frozen from one place and finite from another. Black holes do not just bend light, they bend certainty. They remind you that the universe is not built around the comfort of a single viewpoint. What seems almost stopped from far away may feel like motion from within. What looks like an eternal edge may be crossed in a brief, irreversible moment. What appears dark may be surrounded by some of the most energetic light in the cosmos. So when you hear that black holes can slow time almost to a stop, do not imagine a clock simply dying at the edge of darkness. Imagine instead a message trying to climb out of a place where gravity has made the road upward almost impossibly steep. Imagine its ticks arriving farther and farther apart, its color draining, its brightness fading, until the outside universe receives not an ending, but a silence stretched across time. And perhaps that is what makes black holes so powerful in the human imagination. They are not only places where matter disappears from view, they are places where our simplest beliefs about time, observation, and reality are forced to kneel before something deeper. A black hole says, time is not the same everywhere, sight is not the same as truth, and the universe can contain boundaries where the future itself changes direction. At the edge of such a place, the clock does not merely count seconds. It becomes a question: whose time is real? The one that falls inward, or the one that watches from far away? The vacuum is not truly empty. Nothing may be the hardest thing the universe has ever failed to make. You can empty a room of furniture, pull the air from a chamber, block the sound, cool the walls, seal the glass, and still, you have not created true nothingness. You have only made a quieter kind of something. This is the strange lesson hidden inside the word vacuum. In everyday language, a vacuum sounds like absence. No air, no dust, no visible matter, no pressure, no breath. It sounds like the closest nature comes to a blank page. But in modern physics, the vacuum is not a dead emptiness. It is the lowest energy state of the fields that fill reality. That sentence may sound small, but it changes everything. A field is not a substance like water or smoke, and it is not a simple, invisible fluid floating through space. It is a basic part of how physics describes the universe. Electromagnetic fields, electron fields, quark fields, and other fields are woven into the structure of reality. And particles can be understood as excitations of those fields, like ripples appearing on a surface. Remove the particles, remove the air, remove the obvious contents, and the fields do not vanish. They remain. The vacuum is what those fields are doing when they are as quiet as they can be. But as quiet as possible does not mean perfectly still. At the smaller scales, the vacuum has fluctuations. It trembles with uncertainty. Not because it is chaotic in a messy human way, but because quantum physics does not allow certain properties to be completely settled into perfect zero at the same time. The emptier space is not a frozen silence. It is more like an instrument held at its lowest note, still carrying the possibility of vibration. This is where many popular explanations become careless. You may hear that particles are constantly popping in and out of existence from nothing, as if empty space is a tiny magic show. That image can be useful as a first metaphor, but it can also mislead. These virtual particles are not ordinary little balls appearing from nowhere and disappearing like sparks. They are part of the mathematical language scientists use to describe how fields behave and interact. The real point is not that the vacuum is a box full of tiny visible things. The real point is that empty space has measurable behavior. It affects atoms. It affects forces. It affects light and matter in subtle ways. It can leave marks that experiments can detect. One of the most famous clues is called the Casimir effect. If two extremely smooth metal plates are placed very close together in a vacuum, they can attract each other with a tiny force. This happens because the quantum fields between the plates are restricted differently than the fields outside them, creating a difference that can be measured. The plates are not pulled together by ordinary air pressure because the experiment is done in vacuum conditions. They are influenced by the behavior of the vacuum itself. That is a remarkable thought. Even after removing the obvious contents, empty space can still push and pull in ways that real instruments can record. Another clue appears inside atoms. The energy levels of electrons in atoms are not exactly what a simpler theory would predict, because the vacuum around them is not perfectly inactive. Effects such as the Lamb shift show that the quantum vacuum helps slightly alter the behavior of atomic systems. Even the way an excited atom releases light is connected to the field environment around it. Empty space is not merely the place where physics happens. It participates. It gives the stage a texture. And if you step back from the laboratory into the wider universe, the idea grows even stranger. The space between stars is not truly empty either. It may contain only a few particles in a large volume compared with the dense air around you, but it still contains radiation, magnetic fields, cosmic rays, neutrinos passing almost unnoticed, and the faint leftover glow from the early universe. Intergalactic space is far emptier than anything you experience on Earth, yet it is not absolute nothing. It has temperature, fields, traces, movement, history. The darkness is not blank. It is thinly written. Human beings often imagine nothingness as a clean absence, because our senses are built for solid things, bright things, loud things, things that press back immediately. But reality does not end where perception becomes quiet. The vacuum teaches you that the unseen can still be active, and that silence can still have structure. This does not mean the vacuum is a source of unlimited free energy that can be easily harvested, as some exaggerated claims suggest. The vacuum is not a cosmic battery waiting for anyone to plug into it. Its energy and fluctuations are subtle, constrained by the laws of physics, and not a simple invitation to endless power. The wonder is not that empty space can be used like a fantasy engine. The wonder is that emptiness itself has rules. Even the absence of particles is not the absence of physics. There is a deep humility in that. You can take away more and more, stripping reality down layer by layer, and still something remains. Not a thing in the ordinary sense, not an object you can hold, but a ground state, a restless quiet, a field-filled minimum beneath the visible world. It makes you question what you mean when you say nothing. Is nothing only the absence of what your eyes can find? Is it the absence of air? The absence of atoms? The absence of light? Or would true nothing require the absence of space, time, laws, fields, possibility itself? Physics does not yet hand us a simple answer to that final question, but it does show us that the vacuum we can study is not true philosophical nothingness. It is a physical state, and physical states can have properties. They can be disturbed. They can be measured. They can shape what happens inside them. This turns empty space from a background into a quiet participant in reality. Between your body and the farthest galaxies, between atoms, inside chambers built to remove almost everything, there is no perfect blank. There is the low murmur of fields, the subtle pressure of loud and forbidden vibrations, the delicate evidence of a universe that refuses to become absolutely silent. And maybe this is why the vacuum feels so haunting when you really think about it. We often fear emptiness because we imagine it as meaninglessness, as a place where nothing can happen and nothing can be born. But the physical vacuum suggests something different. Beneath the visible world is not simple absence, but a hidden readiness, a quiet that is not dead, a darkness that still has laws, a silence that can still leave fingerprints. So the next time you look into an empty room or stare into the black spaces between stars, remember that emptiness is not as empty as it seems. The universe does not need to be crowded to be alive with structure. Even when almost everything is removed, reality keeps a faint pulse beneath the surface, as if existence itself is whispering, "There is no ordinary nothing here." Light can push objects without touching them. Light seems weightless because it arrives so gently, but every sunrise is carrying a tiny push. You do not feel it on your face the way you feel wind, because the pressure is incredibly small, spread across your skin too faintly for nerves to notice. Yet it is real. Light can push objects without touching them in the ordinary way, because light carries momentum. A beam of light is not just brightness moving through space. It is energy traveling in a direction, and when that energy is absorbed or reflected by matter, it can transfer a small amount of motion. This is called radiation pressure. And although it sounds almost too delicate to matter, it is one of those hidden rules that becomes powerful when time, distance, and scale grow large enough. A flashlight shining on your hand will not move you across the room. A laser pointer will not shove a wall, but the principle is still there, quietly working. If light hits a surface and is absorbed, it gives that surface a tiny nudge. If it reflects, the change can be even stronger, because the light reverses direction and transfers more momentum to the surface. This means a mirror does not simply return light. It receives a whisper of force from it. The effect is small, but small does not mean unimportant. In space, where there is almost no air resistance, even a tiny continuous push can matter. This is the idea behind solar sails. Large, lightweight reflective sails that use sunlight as propulsion. They do not need fuel in the same way a rocket does. They do not burn chemicals to move forward. Instead, they unfold like shining wings and let photons from the sun press against them, gradually building speed. The push from sunlight is weak, but it never needs to stop as long as the sail remains illuminated. Over time, that gentle pressure can change a spacecraft's path. This is not fantasy. Solar sail missions have already demonstrated the basic idea, showing that light can be used as a real form of propulsion. The beauty of it is quiet. A spacecraft can move because starlight keeps tapping it, patiently, second after second, like rain so soft each drop seems meaningless until the river begins to rise. You can also see the influence of light pressure in the natural shapes of space. Comets, for example, can develop tails that point away from the sun. Part of that behavior comes from the solar wind. a stream of charged particles from the sun, but sunlight itself also pushes dust away, helping create bright dust tails that can stretch across millions of kilometers. Tiny particles feel radiation pressure far more strongly than large objects do, because their mass is small compared with the surface area catching the light. Around stars, radiation pressure can shape dust clouds, influence the movement of small grains, and help sculpt glowing regions of gas and debris. In extreme stars, where the light output is enormous, radiation pressure becomes a major force in the life of the star itself. Inside stars, light produced in the core pushes outward while gravity pulls inward. A star exists in a balance between collapse and pressure, including pressure from radiation and hot gas. In very massive stars, the outward pressure of light can be so intense that it helps drive material away in powerful stellar winds. In the most luminous environments, light is not merely something that reveals matter. It becomes something that moves matter. But this idea also needs honesty, because not every famous light-powered image means what people think. The small glass device called a Crookes radiometer, with black and silver veins spinning under light, is often mistaken as a simple demonstration of radiation pressure. In reality, its motion is mostly caused by thermal effects in the thin gas inside the bulb, not by light pressure alone. True radiation pressure exists, but it is usually much weaker than that spinning toy suggests. This is important because real science becomes more fascinating when it is clean, not when it is exaggerated. Light does push, but nature often hides the push beneath other effects unless the experiment is carefully designed. Scientists have measured radiation pressure directly and use it in precise technologies. In laboratories, highly focused laser beams can trap and move tiny particles using optical tweezers. These tools can hold microscopic beads, cells, or molecules in place with light, not by grabbing them like fingers, but by using the way particles interact with the beam. The light creates forces that can guide small objects towards stable positions. This has become important in biology and physics, allowing researchers to manipulate things far too small for ordinary tools. A beam of light, shaped carefully enough, can become a pair of invisible hands. Lasers can also slow atoms by transferring momentum to them over and over, carefully reducing their motion until they become extremely cold. That may sound impossible, because light usually feels associated with heat, but the key is not ordinary warmth. It is controlled momentum transfer. If atoms absorb photons coming against their motion and then re-emit light in random directions, their movement can be slowed step by step. This is one of the deep surprises of modern physics. Light can heat, illuminate, communicate, cut, measure, trap, cool, and push, depending on how it is used. It is not one simple thing in human experience. It is a carrier of energy and momentum, a messenger that also acts. And maybe that is what makes the subject so quietly mind-changing. You were taught to think of force as something rough, a hand, a shove, a collision, a falling stone, a gust of wind. But light teaches a softer kind of force, one that acts without weight in the familiar sense, without muscles, without visible contact, without sound. It presses so gently that daily life ignores it. Yet in the emptiness of space, it can guide machines, shape dust, influence stars, and become a tool fine enough to hold microscopic life. The universe is full of forces like this, too subtle for the body, but not too subtle for reality. Your senses are tuned to survive on Earth, not to notice the pressure of sunlight on a mirror, or the patient acceleration of a sail between planets. So the world feels still where it is actually being nudged. It feels passive where invisible exchanges are taking place. A beam entering your window in the morning is not only making the room visible, it is also delivering momentum to the surfaces it meets, leaving behind a pressure so small it feels like nothing and so real it can be calculated, measured, and used. There is something almost tender in that. The same light that lets you see a flower can also, in principle, move a grain of dust. The same sunlight that warms a wall can help steer a spacecraft. The same radiation that escapes from stars can push matter across cosmic distances. Light does not need to strike like a hammer to have power. It can work like patience. It can act by persistence. It can move things not by forceful drama, but by endless arrival. So the next time you stand in a sunbeam and feel only warmth, remember that another story is happening too quietly for your skin to name. Countless photons are arriving, touching the world in the language of momentum, pressing on everything they meet with a force almost too small to imagine. And somewhere far above Earth, a reflective sail may be leaning into that same sunlight, proving that even the gentlest thing in nature can become a way forward when it is allowed enough time. Sound can shape matter into patterns. A single note can turn scattered grains of sand into a hidden drawing, as if sound knows a geometry your eyes were never taught to see. At first, sound feels like something that only belongs to hearing. A voice in a room, a chord from a piano, thunder in the distance, the low hum of a machine at night. It seems temporary, invisible, gone as soon as it arrives. But sound is not just an experience inside your ears. Sound is motion passing through matter. It is a traveling pattern of pressure, a wave of compression and relaxation moving through air, water, metal, wood, glass, or almost any material that can vibrate. And because sound is motion inside matter, it can also move matter, organize matter, and sometimes reveal patterns that were already hiding inside vibration itself. This is the real science behind the strange idea that sound can shape matter into patterns. It is not magic. It is not the universe responding to music like a living mind. It is physics, energy moving through a medium, pushing and pulling particles in rhythmic ways. One of the clearest demonstrations comes from a thin metal plate covered with sand. When the plate vibrates at certain frequencies, the sand does not remain randomly scattered. It jumps, slides, and gathers along quiet lines where the plate is barely moving. These are called nodal lines, places where vibration cancels or stays still. The areas between them move more strongly, throwing the sand away. After a moment, the chaos becomes a pattern. Circles, stars, webs, symmetrical shapes that look almost designed. These are often called Chladni patterns, named after Ernst Chladni, who studied them centuries ago and helped make vibration visible. What you are seeing is not sound drawing with intention. You are seeing matter reveal where motion is strong and where motion is calm. The sand becomes a translator. It turns invisible vibration into visible structure. And this teaches a beautiful lesson. Sometimes pattern is not added to matter from outside. Sometimes it appears when matter is placed under the right kind of rhythm. The same principle can happen in water, where sound waves create ripples, standing waves, and complex surface forms. In a shallow dish, different tones can make water tremble into shapes that shift and pulse. In air, strong sound waves can push tiny particles into organized positions. In laboratories, carefully controlled ultrasound can even hold small objects in midair through acoustic levitation. This works because sound waves can create regions of pressure where a small object becomes trapped, suspended not by strings or magnets, but by the force of vibrating air. The object floats in a pressure pattern, held in place by sound energy. It is delicate, precise, and real. Scientists use related acoustic methods to move droplets, sort particles, manipulate tiny biological samples, and study materials without touching them directly. Sound, when controlled carefully, becomes a tool. It can lift, gather, separate, and guide. But it is important to understand the limits. Ordinary music from a speaker will not rearrange heavy objects around your room. A song will not sculpt stone just because it has a powerful emotional feeling. Sound needs a medium to travel through, and its ability to move matter depends on its intensity, frequency, the material involved, and the environment. Loud sound can shake windows because the air pressure changes are strong enough to transfer energy into glass. A singer can break a glass only under special conditions, when the note matches the glass's natural resonance, and enough energy builds up in the vibration. Resonance is the key idea here. Every object has ways it prefers to vibrate depending on its shape, material, and structure. If energy is delivered at the right rhythm, the vibration can grow stronger, the way a swing rises higher when pushed at the right moment. This is why bridges, buildings, instruments, engines, and even small components in machines must be designed with vibration in mind. Sound and vibration are not always gentle. They can organize, but they can also weaken, stress, or destroy if energy builds in the wrong place. A violin string sings because vibration is guided into beauty. A badly designed structure can suffer because vibration is allowed to grow into danger. The difference is not whether vibration exists, but whether it is understood. In nature, vibration is everywhere. The buzzing of insects, the calls of whales through water, the low-frequency rumbles of elephants traveling through the ground, the tremors of earthquakes, the songs of birds, the resonance of caves, the crack of thunder expanding through air. All of these are forms of energy moving through matter. Some are communication, some are warning, some are byproducts of force. But all of them remind us that the world is not still. Even objects that appear quiet can carry hidden modes of vibration. Tap a glass and it rings. Strike a bell and its shape turns impact into tone. Speak in a room, and the walls return echoes based on their surfaces and distances. Your voice does not just vanish, it interacts with the geometry around you. It fills the space, bounces, softens, cancels, overlaps. That is why a cathedral, a small bedroom, a tunnel, and an empty hall do not sound the same. The shape of the environment shapes the sound, and the sound reveals the shape of the environment. There is a quiet exchange between vibration and structure. Matter guides sound, and sound can influence matter in return. This is also why ultrasound, sound above the range of human hearing, is so useful. Doctors use ultrasound imaging because high-frequency sound waves can enter the body, reflect from tissues, and return information that becomes an image. The sound is not heard by you, but it is working. It moves through living matter, bounces differently from different tissues, and helps reveal what eyes cannot see. In other settings, powerful ultrasound can clean delicate objects by creating tiny bubbles in liquid that collapse and help remove dirt. It can also be used in medical treatments to target tissue under controlled conditions. Again, the lesson is not that sound is mystical. The lesson is that vibration is physical, and physical things can be shaped by energy moving through them. What makes this subject so hypnotic is that sound sits between the invisible and the visible. You cannot see a note floating in the air, but you can see what it does when sand gathers into lines, when water trembles into ripples, when a flame flickers near a speaker, when a glass vibrates. When a tiny bead hangs suspended in an acoustic field, sound turns the hidden behavior of matter into a performance. It shows you that the world has patterns beneath the surface, waiting for the right rhythm to expose them. And perhaps that is why these experiments feel so strangely meaningful. They remind you that order does not always come from hands, plans, or drawings. Sometimes order emerges from repeated motion. A wave passes through a plate, and grains find the stillness. A tone fills a chamber, and particles gather where pressure allows them to rest. A vibration enters a string, and a note becomes music. The universe is full of these quiet thresholds, where motion becomes structure and energy becomes form. You live inside them more than you realize. Your own voice is shaped by vibrating vocal cords, air from your lungs, and resonant spaces in your throat and mouth. Your hearing depends on tiny structures responding to vibrations and turning them into nerve signals. Your heartbeat creates rhythms through tissue and blood. Even before you think about music, your body is already a living arrangement of pulses, waves, and responses. So the next time you hear a low hum, a ringing bowl, a deep drum, or rain tapping against a window, remember that sound is not merely something passing through your life and disappearing. It is matter in motion, pressure becoming pattern, energy briefly making the invisible visible. It can draw in sand, lift small objects, reveal hidden structures, and turn empty-seeming air into a sculptor's tool. And maybe the deepest wonder is this: the world does not need to be touched by hands to be shaped. Sometimes it only needs to be given the right rhythm, and matter begins to show the pattern it was waiting to become. Your body glows too weakly for your eyes to see. Your body is glowing right now, not like a lamp, not like a flame, not in any way your eyes can catch, but in a whisper of light so faint that the darkness around you hides it completely. This sounds like a myth at first, the kind of sentence that belongs to fantasy or spiritual exaggeration. But the real science is quieter and more interesting. Human beings emit tiny amounts of visible light, far weaker than what the naked eye can detect. This is called ultra-weak photon emission, sometimes casually called biological light. And it is not the same as the warmth your body gives off in infrared. Infrared radiation is much stronger and comes from your body temperature. Thermal cameras can detect it easily, turning heat into glowing images. But the visible light your body produces is different. It is extremely faint, thousands of times dimmer than your eyes can see, and it comes from chemical reactions happening inside living tissues. You are not shining because you are radioactive in some dramatic way, and you are not glowing because of magic. You are glowing because life is chemistry in motion, and some of that chemistry releases tiny packets of light. Inside your cells, energy is constantly being transformed. Food becomes fuel. Oxygen helps drive reactions. Molecules are built, broken, repaired, and recycled. During normal metabolism, especially processes involving oxygen, cells can produce reactive molecules for brief moments. These molecules are not automatically harmful in small amounts. They are part of ordinary biology, though too much oxidative stress can damage cells. When certain excited molecules return to lower energy states, they can release photons. Most of this light is incredibly weak, scattered, and lost beneath the brightness of the world. But with sensitive cameras in dark laboratory conditions, scientists have measured it. The human body, in other words, is not visually dark. It is simply glowing below the threshold of human sight. That threshold matters. Your eyes are amazing, but they are not perfect instruments for every kind of reality. They evolved to work in daylight, twilight, firelight, moonlight, and ordinary environments where survival depended on contrast, movement, shape, and color. They were not built to detect a few faint photons slowly leaking from skin in a controlled dark room. So the body's glow remains invisible to you, even though it is physically there. This is one of those truths that gently changes the way you imagine yourself. You think of your skin as a surface, a boundary, the outside of you. But on the cellular level, it is also an active landscape of repair, circulation, immune defense, heat exchange, oil production, and molecular activity. Beneath the calm appearance of a hand resting on a table, cells are using oxygen, managing energy, replacing parts, responding to stress, and maintaining order against decay. The faint glow is like a silent side effect of that living effort. It is not a signal your body evolved to send to other human eyes. It is not a visible aura. It is a trace of metabolism, a kind of biological background light produced by the chemistry of being alive. Studies have found that this ultra-weak light can vary across the body and throughout the day. Some measurements suggest it follows a daily rhythm, with emissions changing as metabolism, circulation, and biological clocks shift. The face can show stronger emission than some other areas, likely because of differences in exposure, blood flow, skin structure, and metabolic activity. But this does not mean you can judge someone's health or soul by imagining a glow around them. The effect is too weak, too complex, and too easily misunderstood for that kind of claim. The honest wonder is already enough. Your body emits real visible photons, but so faintly that only specialized instruments can notice. Life, even in its most ordinary form, is never completely dark. This is also true beyond humans. Many living organisms produce ultra-weak light as part of normal biochemical processes. Plants, animals, and microbes can all emit faint photons under certain conditions. Some organisms, of course, glow visibly through bioluminescence, like fireflies, deep-sea creatures, and some fungi. That is a different and much stronger process, usually involving specialized molecules and enzymes evolved to produce light for communication, camouflage, attraction, defense, or hunting. Human ultra-weak emission is not that. You are not a hidden firefly. Your glow is not designed to be seen. It is a faint consequence of internal chemistry, not a lantern with a purpose. And still, there is something deeply moving about it. Because the body often feels solid and familiar from the outside, but inside it is more like a city at night. not glowing with windows you can see, but alive with countless small exchanges. Electrons moving through cellular machinery, oxygen participating in reactions, mitochondria helping manage energy, proteins folding and unfolding, DNA being read and repaired, membranes holding delicate differences between inside and outside. The faint emission of light is like one tiny leak from that enormous invisible labor. It tells you that being alive is not passive. Even when you are still, even when you are asleep, even when you feel like nothing is happening, your body is maintaining a fragile, organized flame of chemistry. Not a flame that burns you, but a controlled chain of transformations that keeps cells alive. And because these transformations are imperfect and dynamic, a little light can escape. The fact that you cannot see it may be the most poetic part. Human life is full of invisible evidence. Your heart's electrical signals do not look like lightning under your skin, but they are there. Your brain's activity does not appear as visible sparks, but it shapes every thought. Your immune system fights without showing a battlefield. Your cells repair damage without asking your attention, and your body's faint glow belongs to that hidden category. Real, measurable, intimate, and almost entirely outside ordinary awareness. It reminds you that reality is not limited to what the senses report. The body you carry through the world is doing things too subtle for you to notice and too important for you to ignore once you learn about them. Every breath feeds chemical reactions. Every meal becomes molecular work. Every night of sleep helps restore systems that were quietly strained through the day. Your glow is not bright enough to guide anyone through a room, but it is bright enough, in principle, to tell science that living tissue is active, reactive, and constantly changing. Researchers are interested in ultra-weak photon emission because it may offer clues about oxidative processes and biological states, though this field must be approached carefully, without turning faint light into exaggerated claims. The truth should remain grounded. Your body emits tiny amounts of visible light because living chemistry sometimes releases photons, and sensitive equipment can detect what eyes cannot. That is already astonishing. It means you are not merely a shape moving through light from the outside. In the faintest possible way, you are also a source of light from within. Not symbolic light, not moral light. Physical light, too weak to see, too soft to warm a room, too subtle to become spectacle, but real enough to measure. And maybe that is why this fact stays in the mind. It gives the body a new kind of dignity. You are not a machine sealed in darkness. You are a living process, a quiet storm of chemistry, a temporary order held together by breath, food, water, repair, and time. Somewhere beneath what you can see in a mirror, tiny flashes are being born and disappearing almost instantly, carrying the signature of cells at work. So the next time you stand in a dark room and see nothing glowing back from your skin, remember that your eyes are not the final judge. The darkness is not proof of absence. Your body is still shining below perception, releasing a faint trace of the life it is constantly spending itself to maintain. You are not bright like a star, and you do not need to be. Sometimes the most honest light is the one too delicate to see, a biological whisper saying that even in silence, even in stillness, even in the dark, life is quietly burning. A magnet can slow falling metal without contact. Drop a strong magnet through a copper tube, and for a moment, gravity seems to lose its confidence. The magnet does not stick to the copper because copper is not ferromagnetic like iron. It does not cling to the wall. It does not grab the metal in the obvious way a fridge magnet grabs a steel door, and yet it falls strangely slowly, drifting downward as if the air inside the tube has thickened into invisible honey. This is one of those experiments that feels like a trick until you understand the hidden conversation happening inside the metal. A falling magnet carries a changing magnetic field with it. As it moves past the copper, that changing field disturbs the electrons inside the metal and makes them circulate in tiny loops called eddy currents. These currents are not planned by the metal, and they are not powered by a battery. They are induced by the motion of the magnet itself. And once those currents appear, they create their own magnetic fields, which oppose the change that caused them. This opposition is described by Lenz's law, one of the most elegant rules in electromagnetism. Nature resists sudden changes in magnetic conditions. So as the magnet falls, the copper responds by producing magnetic effects that push against the motion. Above the magnet, the induced field tends to pull back. Below it, the induced field tends to push upward. The result is not a full stop, but a braking force, a silent magnetic drag that slows the fall without any physical contact. The copper does not need to be magnetized permanently. It only needs to conduct electricity well enough for moving charges to form temporary loops. This is why copper and aluminum can show the effect even though they do not behave like iron around a stationary magnet. If you hold a magnet still beside a copper plate, almost nothing dramatic happens. But move the magnet quickly, and the copper suddenly seems to wake up. Motion is the key. The magnet must create a changing field, because a steady field gives the electrons no reason to circulate in that same way. That is the hidden lesson. The force does not come simply from magnet plus metal. It comes from change. It comes from motion turning into electrical current, and electrical current turning back into magnetic resistance. You are watching energy transform. The falling magnet loses some of its motion energy, and that energy becomes heat inside the copper, usually far too small for you to feel in a simple demonstration, but real. The magnet slows not because gravity has weakened, but because part of the energy of falling is being redirected into tiny electrical currents and then into warmth. This is the same deep principle behind many real technologies. Magnetic braking is used in some trains, elevators, roller coasters, exercise machines, and industrial systems, especially when engineers want smooth braking without ordinary friction pads wearing down in the same way. In certain designs, magnets move near conductive metal, creating eddy currents that resist motion and help slow the system. Because the braking does not rely on surfaces rubbing together, it can be smoother, quieter, and less prone to mechanical wear. But it also has a limitation. Eddy current braking depends on motion. When the motion becomes very slow, the changing magnetic field becomes weaker, the induced currents shrink, and the braking force fades. That is why this kind of magnetic braking can slow something powerfully, but may not hold it completely still by itself. Again, the real truth is better than exaggeration. A magnet is not magically freezing metal in midair. It is creating a temporary electromagnetic reaction that depends on speed, conductivity, field strength, and geometry. The better the conductor, the easier currents can flow. The stronger the magnet, the stronger the induced effects. The faster the motion, the greater the change, and usually the stronger the braking force. The shape of the metal matters too. A closed path lets currents circulate more easily. A tube surrounding a falling magnet can produce a strong, continuous slowing effect because the metal encircles the magnet's path, giving those induced currents room to form. Cut slots into the tube, and the effect can weaken because the current loops are interrupted. This is why the experiment is not just a curiosity, it is a visible doorway into how electricity and magnetism are tied together. A magnetic field can produce electric motion when it changes, and electric motion can produce magnetic fields in return. The two are not separate kingdoms. They are two sides of one deeper relationship. This relationship also explains electric generators. In a generator, motion through magnetic fields induces electrical current. Turn a coil near a magnet or a magnet near a coil, and mechanical motion becomes electrical energy. In the copper tube demonstration, the process is almost like a generator with nowhere useful to send the electricity. The falling magnet induces currents, but instead of powering a lamp, those currents circulate in the metal and dissipate as heat. So the magnet's slow fall is the cost of creating those hidden currents. The universe keeps its accounts carefully. Energy does not simply vanish, it changes form. And if you know how to read the motion, you can see the exchange happening. There is something deeply satisfying about this, because it turns an ordinary fall into a lesson about resistance, not from touch, but from response. The metal does not chase the magnet. It does not choose to oppose it. It follows a rule. When a magnetic environment changes, induced currents arise in a direction that fights that change. If the magnet approaches, the metal reacts in a way that resists the approach. If the magnet leaves, the metal reacts in a way that resists the departure. It is as if the copper dislikes being surprised. Not emotionally, of course, but physically. It pushes back against change. And in that pushback, you can see one of the quiet instincts of nature. Systems often resist being forced too quickly into a new state. This is not only a poetic idea, it is a practical one used in machines, power systems, metal detectors, induction cooktops, and electromagnetic damping devices. An induction cooktop, for example, uses changing magnetic fields to induce currents in compatible cookware, heating the metal directly. Metal detectors sense how conductive objects respond to changing electromagnetic fields. Transformers, motors, and generators all live in the same family of principles, where changing fields and moving charges trade energy in precise ways. The falling magnet is simply the calmest version of a much larger story. It lets you see invisible physics with your own eyes, not by making the field visible, but by making its consequences undeniable. A magnet that should drop quickly instead glides. A metal that should ignore the magnet instead becomes part of the motion. Gravity pulls downward, electromagnetism answers upward, and the fall becomes a negotiation. This is why the demonstration feels almost alive. You see no hand, you hear no engine, nothing touches in the familiar sense. Yet something is clearly slowing the descent. The empty gap between magnet and metal is filled with influence. The tube becomes a quiet machine made from field, motion, and current. And maybe that is what makes the science feel so elegant. It reveals that contact is not the only way the world can act. A changing magnetic field can reach into a conductor and stir its electrons. Those electrons can circulate and create their own field. That field can push back on the moving magnet. Cause and response loop together so smoothly that the falling object seems to enter a different kind of gravity. Slower, softer, more thoughtful, but nothing supernatural has happened. The laws are enough. The hidden currents are enough. The metal is not passive. It is responsive. The magnet is not simply falling. It is leaving a moving disturbance behind it. So the next time you see a magnet slide slowly through copper or hover strangely above a spinning metal disc, remember that you are watching invisible motion become visible through delay. You are seeing electrons stirred into loops, energy redirected into heat, and nature enforcing a quiet rule against sudden magnetic change. The magnet falls, but not freely. The metal answers, but without touching. And in that slow descent, reality reveals one of its most beautiful secrets. Sometimes the strongest resistance is not a wall in the way, but an invisible pattern waking up just in time to push back. Water can climb up, thin tubes against gravity. A glass tube thinner than a hair can make water rise as if it has quietly decided that gravity is only a suggestion. You expect water to fall, to spill downward, to seek the lowest place it can find. That is what rain does on a window, what rivers do through valleys, what a dropped cup does across the floor. But place water near a very narrow tube, or inside the tiny spaces of a paper towel, a sponge, soil, or the vessels of a plant, and something stranger begins to happen. The water climbs, not with muscles, not with pumps in the ordinary sense, not because gravity disappears, but because the forces acting at small scales can become stronger than the pull you normally notice. This is called capillary action, and it is one of the quiet reasons life can exist on land. At the heart of it are two simple tendencies. Water molecules are attracted to each other, and water molecules can also be attracted to other surfaces. The attraction between water molecules is called cohesion. It is why droplets hold together, why water beads on some surfaces, why the surface of a pond can behave like a delicate skin. The attraction between water and another material is called adhesion. It is why water can cling to glass, paper, plant tissue, or the inside of a thin tube. When water touches a narrow glass tube, the molecules near the wall are drawn toward the glass. They begin to creep upward along the surface. Because water molecules also hold on to one another, the rising molecules pull neighboring molecules with them. The narrower the tube, the more important the walls become compared with the amount of water inside. In a wide cup, gravity dominates the visible shape, and the surface looks mostly flat. In a very thin tube, the surface forces are no longer a small detail. They become the main actors. The water curves upward at the edges, forming a meniscus, that small curved surface you may have seen in a measuring tube without realizing it was telling a story. The liquid rises until the upward pull from adhesion and surface tension is balanced by the weight of the water column. It does not climb forever. Nature is not cheating. It climbs only as far as the forces allow. But the fact that it climbs at all is enough to make the everyday world feel different. A paper towel drinking up a spill is not just absorbing water in a vague way. Its fibers contain countless tiny spaces, and those spaces behave like capillaries. Water clings to the fibers, pulls itself along, and spreads through the material. A sponge works through a similar idea, with tiny channels and surfaces guiding liquid inward. Soil holds and moves water partly because of the narrow spaces between particles. This is why dry ground can draw moisture upward from below, why plant roots can access water held in small pores, and why the texture of soil matters so much for farming and ecology. Sand, clay, and loam do not handle water the same way because the sizes and shapes of their tiny spaces differ. Clay can hold water strongly because its particles are small and its spaces are tiny, while sandy soil drains more easily because the gaps are larger. Capillary action is not a decorative detail in nature. It helps decide where water stays, where it travels, and how living systems survive. In plants, the story becomes even more beautiful, though also more complex. Capillary action helps water move through narrow spaces, but tall trees do not lift water from roots to leaves by capillary action alone. That would not be enough for the tallest trees. Plants also rely on transpiration, the loss of water vapor from leaves, which creates a pulling tension through the continuous water columns inside xylem vessels. Water molecules cling together through cohesion, and as water evaporates from the leaves, it helps pull more water upward from the roots. Adhesion to the vessel walls helps stabilize the column. Root pressure can contribute in some plants under certain conditions, but the main upward movement in tall trees is often explained by this cohesion tension process. That means a tree is not simply pumping water like a machine with a motor. It is using the physics of evaporation, molecular attraction, and narrow internal pathways to move water upward against gravity. Every leaf is part of the system. Every tiny pore on the leaf surface participates in a trade. The plant takes in carbon dioxide for photosynthesis, but it loses water vapor in the process. That loss becomes part of the pull that draws water from the ground. In a forest, water is not only falling as rain, it is also climbing invisibly through trunks, branches, veins, and leaves, carried by forces too small for your hand to feel, but powerful enough to feed entire canopies. This is one reason a tree can stand as a kind of living fountain, quietly raising water from the dark soil into sunlight. The same principle appears in things humans make. Fountain pens use capillary action to control ink flow through narrow channels. Medical test strips can draw blood or fluid along tiny paths without a pump. Microfluidic devices, sometimes called labs on chips, use small channels to move droplets for analysis, taking advantage of how fluids behave differently when the spaces are very small. Wicks in candles and oil lamps lift liquid fuel upward so it can burn at the flame. If you have ever watched the edge of a cloth darken as it pulls water from one side to the other, you have seen small-scale physics doing patient work. The liquid is not thinking. It is following attractions, surfaces, and geometry. And this is where the wonder becomes practical. At large scales, gravity often rules your intuition. Buckets spill downward. Waterfalls descend. Oceans settle into basins. But at small scales, surface forces can dominate. A tiny droplet can cling beneath a leaf. Water can crawl through paper. A plant can maintain delicate columns of liquid inside microscopic tubes. An insect can stand on the surface of a pond because surface tension supports it. The world changes depending on scale. What is weak in one setting becomes powerful in another. This is one of the most important lessons in science. The rules do not disappear, but their importance shifts. Gravity is still present in a thin tube. It is still pulling the water downward. But adhesion and cohesion are strong enough over that tiny distance to pull upward until balance is reached. Your senses, built for the size of your body, often miss this shift. You see water rise, and it looks almost defiant, but it is not defying nature. It is revealing a part of nature you usually overlook: the shape of a surface, the width of a gap, the chemistry of a wall, the attraction between molecules. These small details decide the movement of liquids in ways that can seem impossible from the human scale. And perhaps this is why capillary action is so quietly satisfying. It shows that the world is not controlled only by obvious forces. The gentle cling of water to glass can matter. The microscopic spaces inside paper can matter. The hidden vessels of a leaf can matter. Entire living systems depend on tiny attractions repeated billions of times. A forest may look like trunks, branches, and green crowns, but inside it, there is a silent vertical river, drawn upward by evaporation and held together by molecular loyalty. A seedling rising from the soil is also a lesson in fluid physics. A towel soaking up a spill is a miniature landscape of channels. A drop spreading through cloth is a map of invisible pathways, becoming wet one fiber at a time. There is no need to exaggerate the truth. Water does not climb endlessly. It does not ignore gravity. It does not move by intention. But within narrow spaces, it can rise, creep, spread, and feed life, because small forces become large when the world becomes small enough. That is the real miracle. Not a violation of physics, but a rearrangement of importance. So the next time you see water soak into paper, or notice moisture climbing the edge of a napkin, or look at a tree lifting water higher than any human could reach with a straw, remember that you are watching the hidden power of surfaces. Gravity pulls downward, but the walls whisper upward. Molecules hold to molecules. Surfaces call to liquid. And the water follows a path that seems impossible only until you understand the scale. In that quiet climb, reality offers one of its gentlest lessons. Sometimes the forces that move the world are not the loud ones. Sometimes they are small attractions, repeated patiently, lifting life upward one invisible step at a time. A drop of water can hover on a hot pan. A drop of water on a very hot pan can survive longer than a drop on a merely hot one, and that is where common sense begins to slip. You expect heat to destroy water faster. You expect a hotter surface to mean quicker boiling, sharper sizzling, instant disappearance. And if the pan is warm or moderately hot, that is exactly what happens. The water spreads, sizzles, breaks apart, and evaporates quickly as heat flows directly into it. But when the surface becomes hot enough, something unexpected appears. The bottom of the droplet vaporizes so rapidly that it creates a thin cushion of steam between the liquid water and the metal. Instead of touching the pan fully, the droplet begins to ride on its own vapor. It skates, trembles, rolls, and sometimes seems to hover. Not because gravity has stopped, and not because the water has become weightless, but because a layer of gas is holding it away from the surface that should be destroying it. This is called the Leidenfrost effect, and it is one of those rare pieces of physics that looks like a magic trick, but becomes even more beautiful when you understand it. The pan is hot enough to boil the droplet's underside instantly, but that instant boiling creates steam, and steam is a poor conductor of heat compared with direct contact with metal. So the very heat that threatens the droplet also protects it for a short time. The water forms its own shield from the fire. It is not perfectly safe, not permanent, not mystical, but temporary and real. A small liquid body surviving on a cushion made from its own disappearance. You can often recognize the effect by the sound. On a pan that is hot but not extremely hot, a drop of water makes a fierce hiss because it touches the surface more directly and boils violently. On a hotter pan, the droplet may become quieter, bead up, and glide around with a smoother motion. The silence is part of the clue. Less contact means less direct boiling at the surface. The droplet is still evaporating, but more slowly than you might expect because the vapor layer insulates it. This is why cooks sometimes flick water onto a pan to judge its heat. If the water splatters and vanishes, the pan is hot. If the droplet beads and dances, the surface may be very hot, high enough for the Leidenfrost effect to begin. But this kitchen test should be treated carefully because the exact temperature depends on the surface, the pan material, roughness, cleanliness, and the liquid involved. There is no single magical number that applies perfectly everywhere. A smooth metal pan, a rough pan, a dirty surface, a different liquid, or changes in pressure can all shift the behavior. The real principle is not a fixed temperature, but a balance between heat transfer, boiling, vapor production, and the ability of the vapor to stay trapped under the droplet long enough to lift it. That vapor cushion is incredibly thin, but it changes everything. It reduces friction, allowing the droplet to move easily. It reduces heat flow, allowing the droplet to last longer. It can even make the droplet vibrate, wobble, or break into smaller droplets as steam escapes unevenly beneath it. If the surface has tiny grooves or patterns, the vapor can be guided in certain directions, causing droplets to move like little self-propelled beads. Researchers have studied this not only because it is visually fascinating, but because it matters in engineering, cooling systems, metal processing, and safety. When a surface is extremely hot and a liquid cannot touch it properly because of a vapor blanket, cooling can become less effective. This is a serious issue in situations where hot materials must be cooled quickly, because the insulating vapor layer can slow down heat removal. In other words, the Leidenfrost effect is not just a party trick on a stove. It can influence how hot metal cools, how droplets behave in engines or industrial systems, how liquids interact with overheated surfaces, and how engineers think about heat transfer under extreme conditions. It also appears with other liquids, not only water. Liquid nitrogen, for example, can skitter across a floor or surface as it rapidly boils and creates a vapor layer beneath itself. This is one reason very cold boiling liquids can sometimes appear to glide strangely when spilled, though they are dangerous and should never be treated casually. The same basic idea can happen whenever a liquid meets a surface so much hotter than its boiling point that vapor forms fast enough to separate the two. What makes water on a pan feel so memorable is that it brings this extreme behavior into an ordinary place. A kitchen becomes a laboratory. A droplet becomes a lesson in phase change. A hot surface becomes a reminder that contact is not always as simple as it seems. The droplet appears to hover because it is caught between two states: liquid above, gas beneath, heat below, evaporation all around. It is constantly losing itself to vapor, but that vapor is the reason it remains for a little while. There is a strange poetry in that, but the science stays clear. The droplet is not defying heat. It is responding to heat in a way that temporarily changes how heat reaches it. Direct contact would destroy it faster. Separation lets it endure. And this creates one of the most surprising lessons in thermal physics. Sometimes adding more heat can reduce immediate heat transfer because the system reorganizes itself and places an insulating layer in the way. This kind of reversal is why science matters. The world does not always follow the simple line your intuition draws. More heat does not always mean faster evaporation in the way you first imagine. More danger can sometimes create a barrier. More intensity can sometimes produce a strange kind of protection. But that protection has limits. As the droplet shrinks, changes shape, and loses mass, the vapor layer shifts. Eventually the water evaporates completely. The hover ends. The tiny skater vanishes. Nothing has escaped the laws of physics. It has only taken a more surprising path through them. And perhaps that is what makes the Leidenfrost effect so hypnotic. It shows you a liquid refusing to behave like a passive victim of heat. It beads itself together, lifts itself on steam, and moves across a surface that should have swallowed it immediately. It is a reminder that matter is not only defined by what it is, but by the conditions around it. Water in a glass is calm. Water in a cloud floats as droplets. Water in a kettle becomes steam. Water on an extremely hot pan becomes a tiny hovercraft, supported by the vapor of its own boiling. Same substance, different world, different behavior. The pan does not merely heat the droplet, it changes the rules of contact between them. And in that small moment, you can see a larger truth about nature. Boundaries matter, layers matter, transitions matter. The most important thing is sometimes not the object itself, but the thin, invisible region where two states meet: liquid and gas, heat and cooling, contact and separation, survival and disappearance. So the next time a drop of water lands on a hot pan and suddenly gathers into a shining bead, do not see it as a simple kitchen detail. See it as a tiny demonstration of how reality can surprise you at the edge of change. The droplet is not floating because the world has become less real. It is floating because the world is more subtle than it looks. Beneath it, a cushion of steam is being born and destroyed every moment, holding the water just above the heat, letting it dance briefly over the thing that is slowly ending it. And maybe that is why the image stays in the mind. A drop of water, fragile and temporary, surviving not by resisting transformation, but by using transformation itself as the space beneath its feet. Some materials remember their original shape. Bend a piece of certain metal until it looks ruined. Warm it gently, and it can return to its old form as if the shape was never lost. That sounds like memory, but not the kind stored in a brain. It is not thought, not awareness, not a hidden desire inside matter. It is structure remembering structure. Some materials can be deformed and then recover their original shape when temperature changes, because their atoms or molecules are arranged in a way that allows them to shift between different internal forms. These are called shape memory materials, and the most famous examples are shape memory alloys, especially nickel-titanium alloy, often called nitinol. At first it feels impossible. How can a bent wire know how to become straight again? The answer is that the material was trained or manufactured into a certain shape at a high temperature phase, and when cooled, it can be bent more easily into another shape without breaking its internal order completely. Then, when heated past a certain transition temperature, the internal crystal structure changes back, and the material returns toward the form it had before. The shape is not stored like a photograph. It is stored in the arrangement of atoms and the way that arrangement can transform. In one phase, the material is more easily deformed. In another phase, it becomes stronger and pulls itself back into its trained shape. The names scientists use for these phases can sound technical, but the idea is simple enough to feel. The same material can have two different internal personalities depending on temperature. In the cooler state, it can be bent and rearranged. In the warmer state, it tries to restore its original geometry. This is why a thin shape memory wire can be twisted, folded, or stretched, then placed in warm water and seen curling back like something waking from sleep. But it is not waking, it is transforming. The atoms are shifting from one organized pattern into another, and the visible motion is the large-scale result of countless microscopic changes happening together. What makes this so useful is that the movement does not require gears, motors, or complicated machinery. Heat itself becomes the trigger. A small change in temperature can produce motion, force, or recovery. This is why shape memory alloys have found roles in medicine, aerospace, robotics, engineering, and everyday devices. Nitinol stents, for example, can be compressed into a small form, inserted into a blood vessel, and then expand at body temperature to help hold the vessel open. In that case, the material's ability to recover shape is not a trick. It becomes a medical tool. Some eyeglass frames made from shape memory alloys can bend and spring back instead of snapping easily. In orthodontics, certain wires can apply gentle, steady force as they try to return to a programmed shape, helping move teeth over time. In aerospace systems, small actuators made from shape memory materials can change position with heating, offering motion in places where lightweight, compact mechanisms are valuable. The material is not alive, but it behaves in a way that feels almost biological because it responds to conditions. It carries a kind of physical instruction inside itself. When the environment reaches this temperature, become this shape again. There are also shape memory polymers, which work differently from metals, but can also be designed to return to a previous form when triggered by heat, light, moisture, or other conditions. These polymers may be stretched or folded into a temporary shape, then recover when their molecular chains gain enough freedom to move back toward the stored arrangement. Some are being explored for biomedical devices, self-deploying structures, soft robotics, textiles, and materials that can adapt after installation. The phrase memory is useful because it gives your imagination a handle, but it must be used carefully. These materials do not remember experiences. They do not learn in the human sense. They do not decide. Their memory is written into energy landscapes, internal structure, and phase changes. They return because one arrangement is favored under certain conditions, and the material follows that path when the trigger arrives. That makes the phenomenon more honest and, in a way, more impressive. No consciousness is needed. No magic is needed. Matter itself, when arranged precisely, can hold a recoverable form. The difference between ordinary bending and shape memory recovery is important. If you bend a normal paperclip too far, it stays bent because defects and permanent changes accumulate inside the metal. You have damaged the arrangement beyond simple return. But in a shape memory alloy, deformation can happen through a reversible rearrangement of the crystal structure, at least within limits. Push it too far, overheat it, fatigue it through too many cycles, or use it outside its designed range, and it can fail like any real material. The memory is powerful, but not infinite. It has boundaries. It has a lifetime. It depends on composition, processing, temperature, stress, and the exact way the material was trained. That is another reason the real science is more interesting than the myth. The effect is not a miracle that ignores damage. It is a carefully engineered balance between flexibility and return. Some shape memory alloys also show superelasticity, where they can bend dramatically and spring back without needing a separate heating step, as long as they are used at the right temperature. In that case, stress itself triggers an internal phase change, and when the stress is removed, the material returns. This is why certain nitinol components can survive large deformations that would permanently bend ordinary metals. They are not simply stronger in the normal sense. They are using a reversible internal transformation as a way to absorb and release strain. Imagine a bridge inside the material, not a physical bridge you can see, but an internal pathway between two atomic arrangements. Ordinary materials may be forced into damage when pushed. Shape memory materials, within their limits, can move along that pathway and come back. This changes how you think about objects. A material is not just what it looks like from the outside. Its true behavior is hidden in its internal architecture. Two wires can appear similar, but one may stay bent while the other returns. Two plastics can feel similar, but one may soften, unfold, and recover a programmed form. The secret is not in appearance, it is in structure. It is in the way matter was made, cooled, heated, stretched, trained, and allowed to transform. And this gives shape memory materials a strange emotional resonance. They remind you that form is not always as fixed as it seems. A thing can be bent without being permanently broken. A temporary shape can hide a deeper one. A material can carry a pattern that only reappears under the right conditions. Of course, human healing is not the same as metal returning under heat, and we should not force the metaphor too far. But the image remains powerful because it is grounded in real physics. Recovery can be built into structure. Return can be prepared before deformation happens. Resilience can be engineered at the microscopic level. In laboratories, this idea continues to grow. Researchers study materials that change shape in response to electrical current, body temperature, sunlight, magnetic fields, humidity, or chemical environments. The dream is not only to create materials that go back to old shapes, but materials that can adapt, deploy, seal cracks, open passages, grip objects, release medicine, or respond intelligently to surroundings without needing bulky machines. A tiny device might unfold inside the body. A spacecraft component might open after launch. A soft robot might curl, crawl, or grip with heat-driven motion. A fabric might tighten or loosen with changing conditions. The line between object and mechanism becomes thinner. The material itself becomes part of the machine. That may be the deepest shift. For most of history, humans built motion by adding parts. Hinges, wheels, springs, ropes, motors. Shape memory materials suggest another path, where motion is not added to matter but written into matter. The object does not need a separate engine to change. Under the right trigger, the material becomes the engine. And when you see a crumpled wire straighten in warm water, you are watching that idea in miniature. A hidden instruction becomes visible. A microscopic rearrangement becomes macroscopic movement. A silent structure announces itself through form. So the next time you think of matter as passive, as dead stuff waiting to be pushed, remember that some materials carry a reversible past inside them. They can bend, wait, and return. They can seem ruined, then recover. They can hold a shape not because they remember like you do, but because nature allows memory to exist in more than one language. In a brain, memory is electrical and chemical. In a material, it can be crystalline, molecular, thermal, mechanical. And in that quiet return from distortion to form, you see one of the most surprising truths of the physical world. Matter does not have to be alive to have a past written into it, and sometimes all it takes to reveal that past is a little warmth. A liquid can turn solid when hit. A bowl of liquid can let your fingers sink slowly, then resist a punch as if it has suddenly grown bones. That is the strange behavior behind fluids that seem to turn solid when hit. And the most familiar example is a simple mixture of cornstarch and water, often called oobleck. Stir it gently, and it flows like thick cream. Press into it slowly, and your hand can move through. But slap it hard, squeeze it quickly, or try to run across a pool of it, and it stiffens beneath the sudden force. For a moment, the liquid behaves almost like a solid, not because it has frozen, not because a chemical reaction has transformed it into a new material, and not because it has broken the rules of matter, but because the particles suspended inside it have jammed together under stress. This is called shear thickening. Shear simply means layers of material sliding past one another, and thickening means the fluid becomes more resistant to flow when that sliding happens quickly or forcefully. In an ordinary liquid like water, pushing harder usually just makes it move faster. In a shear thickening fluid, pushing harder can make it fight back. The reason lies in its crowded inner structure. Cornstarch particles are tiny solid grains suspended in water. When you move slowly through the mixture, the water has time to help the particles slide around each other. The grains can rearrange, separate, and flow. But when you hit the mixture suddenly, the particles do not have enough time to move neatly out of the way. They collide, press against one another, and form temporary force chains, like a crowd of people suddenly packed so tightly in a doorway that no one can move. The water that once helped them slide becomes trapped between them, and the whole mixture stiffens. The liquid has not truly become a permanent solid. It has entered a brief stressed state where the particles lock together until the force eases. Then the structure relaxes, the grains loosen, and the material flows again. This is why oobleck feels almost alive in your hands. Hold it gently, and it drips between your fingers. Strike it, and it resists. Let it rest, and it softens. It is not deciding. It is responding to the speed and strength of deformation. The same material carries two different personalities depending on how you treat it. This makes shear thickening fluids powerful teaching tools, because they reveal something your everyday senses often hide. A material is not always defined by one fixed label like liquid or solid. Its behavior can depend on conditions. Time matters, force matters, speed matters. A slow world and a sudden world are not the same world for the particles inside the fluid. Under gentle motion, the mixture has enough freedom to rearrange. Under impact, it becomes crowded, locked, and resistant. That difference is not just a kitchen curiosity. Scientists and engineers study shear thickening materials because they may be useful in protective gear, shock absorbers, sports equipment, and industrial processes. Some body armor research has explored fabrics treated with shear thickening fluids, where the material remains flexible during normal movement but stiffens when struck. The idea is elegant. Protection that is soft when you need comfort and hard when you need defense. The fluid does not replace strong fibers such as Kevlar, but it can work with them, helping distribute impact and limiting sudden motion. Similar principles may help design damping systems. protective pads, and materials that respond intelligently to force without electronics or motors. But this behavior can also cause problems. In factories, thick suspensions of particles in liquid can suddenly become difficult to pump or mix if stress conditions change. A material that flows smoothly at one speed may jam at another, making processing harder. So shear thickening is both useful and troublesome, depending on whether you understand it. This is often how real science works. The same effect can be a tool in one place and a challenge in another. The key is control. The particles, the liquid, the concentration, the surface chemistry, and the force all shape what happens. A watery mixture with too little cornstarch will not stiffen dramatically. A mixture packed with enough particles can. The grains must be close enough to interfere with one another under stress. If there is too much room, they move freely. If there is just the right crowding, impact can turn motion into a jam. This is why the recipe matters, and why not every thick liquid behaves this way. Honey is thick, but it does not become solid when punched in the same manner. Ketchup, paint, and blood can have complex flow behaviors too, but different ones. Some fluids become thinner when stressed. Some hold shape until pushed. Some flow slowly over time. The world of fluids is far richer than the simple category liquid suggests. Oobleck is only one doorway into that hidden variety. It shows that flow is not weakness, and stiffness is not always permanent. A substance can be soft under patience and strong under violence. And there is something quietly philosophical in that, as long as we keep the science honest. The mixture teaches that response depends on how force arrives. Slow pressure gives the system time to adapt. Sudden impact creates resistance. In the fluid, this is not emotion. It is particle physics at a human scale. But the image stays with you because it feels familiar. There are systems in nature, in machines, even in bodies, that behave differently under sudden stress than under gentle change. Bones, muscles, sand, soil, crowds, traffic, and materials all have thresholds where smooth motion becomes locked motion. Oobleck lets you see that threshold with your own hands. It makes an invisible idea visible. Structure can appear only when pressure demands it. And yet, the lesson is not that the liquid is secretly solid. It is that solidity and liquidity are sometimes behaviors, not identities. The same mixture can flow or resist depending on the moment. It can spill like a liquid, then brace like a shield, then melt back into softness without ever changing its basic ingredients. This challenges the way we name the world. We like categories because they make reality feel stable. Solid, liquid, soft, hard, safe, fragile. But nature often lives between categories, shifting not through magic, but through conditions. A material is not only what it is made of, it is also how its parts are arranged, how crowded they are, how quickly they are forced to move, and how much time they have to respond. So the next time you see a hand slap a pool of cornstarch and water and bounce away from what should have splashed, do not see it as a trick liquid pretending to be a solid. See it as a crowd of tiny particles suddenly locking together under pressure, then loosening when the pressure passes. See it as a reminder that the ordinary word liquid hides an entire world of behavior. And maybe that is why this simple mixture feels so unforgettable. It shows you that matter is not always loyal to the names we give it. Sometimes it waits for the force, reads the speed of the moment, and answers in a completely different language. Superconductors can make magnets levitate. A small magnet can hang above a cold ceramic disc as if gravity has misplaced it, floating in silence with no string, no air jet, no hidden hand. The first time you see a superconductor make a magnet levitate, it feels like a trick from a world where ordinary rules have softened. But the truth is not that gravity disappears. The truth is that another force becomes organized enough to hold gravity back. Superconductors are materials that, under the right conditions, allow electric current to flow with zero electrical resistance. In an ordinary wire, electrons moving through the material lose energy as heat because they scatter from atoms, defects, and vibrations inside the structure. That is why electronics warm up, why power lines waste energy, why resistance is part of daily technology. But in a superconducting state, the material enters a radically different phase. Electrical resistance drops to zero, and currents can flow without gradually fading away in the normal way. This alone is strange enough, but superconductors do something even more visually shocking. They can push magnetic fields out of their interior. This is called the Meissner effect. When a material becomes superconducting, it does not simply become a perfect conductor, it actively rearranges its surface currents so that magnetic fields are expelled from within. If a magnet is placed above a superconductor, the superconductor responds by creating currents that generate an opposing magnetic field. The result can be a repulsive force strong enough to lift the magnet, balancing its weight. The magnet floats not because it has escaped Earth, but because invisible electromagnetic forces are pushing upward as gravity pulls downward. It is a balance, not a miracle. Yet the balance is so clean and quiet that it feels almost unreal. In many demonstrations, a small magnet hovers above a cooled superconductor, or a superconducting puck glides above a magnetic track, holding itself in place even when tilted. This second behavior reveals something deeper than simple repulsion. Many superconductors used in demonstrations are Type II superconductors, and they allow tiny threads of magnetic field to pass through in controlled regions called flux vortices. These magnetic threads can become pinned by imperfections in the material, locking the superconductor's position relative to the magnetic field. This is called flux pinning, and it is the reason a superconducting object can appear not just to float, but to stay fixed in space above or below a track, almost as if it remembers where it belongs. It can hang upside down beneath a magnetic rail or glide around a circular path without falling off, because the magnetic field lines are pinned in place inside the superconductor's structure. The object is not free-floating in the way a balloon floats. It is magnetically anchored. It has invisible rails made of field patterns. This is why superconducting levitation can look more stable than simple magnetic repulsion between ordinary magnets, which often flip, slide, or become unstable. Flux pinning gives the system a kind of locked geometry. The superconductor resists changes in its magnetic relationship, so if you push it slightly, it tends to return toward its pinned position. It is as if the material is holding a memory of the magnetic field configuration, though again, not memory in a conscious sense. It is memory written in currents, fields, and defects inside the cooled material. But there is a catch that keeps this technology from being everyday magic. Most superconductors only work at very low temperatures. Many classic superconductors must be cooled close to absolute zero, while some high-temperature superconductors work at temperatures reachable with liquid nitrogen, which is still extremely cold compared with everyday life. Liquid nitrogen boils at a temperature far below the coldest winter on Earth. And when you see a superconductor smoking in a demonstration, that white vapor is not smoke from burning. It is moisture in the air condensing as the liquid nitrogen cools everything around it. Without that cooling, the material returns to its ordinary state, resistance comes back, and the special magnetic behavior disappears. The levitating magnet falls. The spell ends because the phase has ended. This is one of the great challenges in superconductivity research. Scientists have found materials that superconduct at higher temperatures than early discoveries, but practical room temperature superconductivity under ordinary conditions remains one of the most difficult goals in physics and materials science. There have been dramatic claims over the years, but extraordinary claims require careful confirmation, and many have not held up under independent testing. The grounded truth is still astonishing. Superconductivity is real, powerful, and already useful, but it usually demands extreme cooling or special conditions. It is not yet a simple material you can place in your pocket and use at room temperature to float objects around your room. Still, even with this limitation, superconductors matter enormously. They are used in powerful magnets for MRI machines, particle accelerators, certain research instruments, and experimental energy systems. Superconducting magnets can create strong magnetic fields efficiently because currents can persist with very little loss once established. In transportation, magnetic levitation trains can use magnetic forces to reduce friction and allow smooth, high-speed motion. though not all maglev systems rely on superconductors in the same way. Some use ordinary electromagnets, some use permanent magnets, and some experimental designs use superconducting components for stability and lift. The broader dream is clear. If resistance could be removed from electrical systems more easily, energy could move with far less waste. Motors, generators, power grids, sensors, computers, and transportation systems could change, but dreams must meet engineering. Cooling costs, material brittleness, current limits, magnetic field limits, manufacturing difficulty, and safety all matter. Superconductors are not magic shortcuts around reality. They are reality revealing a deeper set of possibilities under strict conditions. What makes levitation so powerful as an image is that it turns an invisible quantum state into something your eyes can understand. You cannot see electrons pairing. You cannot see resistance vanish. You cannot see surface currents arranging themselves. You cannot see magnetic flux pinned in microscopic regions, but you can see a magnet floating. You can see the space between object and surface. You can see gravity being answered by a force you cannot touch. That visible gap becomes a doorway into the hidden behavior of matter. It reminds you that materials are not fixed by their ordinary appearance. A ceramic-looking disc cooled to the right temperature can enter a state where electricity moves differently and magnetism behaves in ways that seem impossible at room temperature. The same object warmed up becomes ordinary again. Temperature does not merely make things hot or cold. It can decide what phase of reality a material is allowed to occupy. Ice, water, and steam already teach this in a familiar way. But superconductivity pushes the idea into a stranger domain. It shows that cooling can reveal forms of order that heat normally destroys. At higher temperatures, internal motion disrupts the delicate collective behavior needed for superconductivity. At low temperatures, the material can settle into a coherent state where electrons act in coordinated ways rather than as isolated scattered particles. The details are complex, and different superconductors work through different mechanisms. But the emotional lesson is simple. Matter can become more organized than your everyday intuition expects. And when that organization appears, the impossible looking becomes natural. A magnet floats, a current persists, a field is expelled or pinned. The ordinary world opens a hidden layer. So the next time you see a superconducting magnet levitate, do not think of it as a violation of gravity. Think of it as a conversation between gravity and electromagnetism, with quantum order quietly tipping the balance. The magnet still has weight, the Earth still pulls, but the superconductor, cooled into its rare state, answers with currents that do not fade and fields that refuse to enter freely. Between the magnet and the material is a gap filled not with emptiness, but with rules. And maybe that is why the sight feels so haunting. It shows that the world can look solid and ordinary for years, then under the right conditions reveal a behavior so elegant it feels like nature kept it hidden for anyone patient enough to cool matter down and watch it rise. Plasma is not solid, liquid, or gas. A flame, a lightning bolt, the sun, and the glowing letters of a neon sign all point toward a state of matter that refuses to fit neatly into the childhood list of solid, liquid, and gas. You were probably taught that matter comes in three familiar forms. Solid keeps its shape. Liquid flows while keeping volume. Gas spreads to fill a space. That lesson is useful, but it is not complete. Heat a solid enough and it can melt into liquid. Heat a liquid enough and it can become gas. But if a gas receives enough energy, something more dramatic can happen. Some of its atoms lose electrons, and the gas becomes a mixture of charged particles. This charged state is called plasma. It is often described as the fourth state of matter, though scientists know there are other exotic states too, especially under extreme conditions. Plasma is different from an ordinary gas because its particles are no longer mostly neutral. It contains freely moving electrons and positively charged ions, and that changes everything. A normal gas may drift, expand, and bump around, but plasma can conduct electricity, respond strongly to electric and magnetic fields, form filaments, glow, twist, stream, and behave collectively in ways that make it feel almost alive. The key word is collectively. In a gas, particles mostly act like individuals, colliding and moving in random directions. In plasma, because many particles are charged, each movement can influence many others through electromagnetic forces. The result is a material that can carry currents, create magnetic fields, and organize itself into patterns. This is why plasma is not simply very hot gas, even though heat is one way to create it. Some plasmas are extremely hot, like the material inside stars, where atoms are stripped apart and nuclear fusion can occur. Other plasmas can be cooler in everyday terms, such as the glowing gas inside certain lamps, where the electrons may be energetic enough to excite atoms and create light, while the overall tube does not feel like the surface of a star. The word plasma covers a wide range of conditions, from the thin plasma of the upper atmosphere to the blazing cores of stars, from laboratory fusion experiments to industrial plasma cutters, from auroras waving near Earth's magnetic poles to the glowing trails inside discharge tubes. What unites them is not one temperature or one color, but the presence of charged particles acting together. The sun is the most familiar plasma in your life, even though you never touch it and rarely think of it that way. Its visible surface and deeper layers are made of hot, ionized material, constantly shaped by magnetic fields, convection, radiation, and fusion in the core. Solar flares and prominences are not ordinary flames in space. They are enormous plasma events guided and twisted by magnetic structures. A loop of glowing material can rise from the sun and follow invisible magnetic arcs, showing that plasma is tied to fields in a way ordinary neutral gas is not. Lightning is another brief and violent example. During a lightning strike, air is heated and ionized along a path, creating a channel of plasma that conducts electricity between cloud and ground or within clouds. That channel glows because atoms and molecules are energized and then release light. Thunder comes after because the heated air expands explosively, sending a pressure wave outward. So lightning is not just a bright line. It is air transformed for an instant into a conducting path, a temporary plasma bridge through the sky. Auroras are gentler to look at, but their origin is also tied to charged particles. Particles from the sun interact with Earth's magnetic environment and upper atmosphere, exciting atoms and molecules high above the surface. As those atmospheric particles relax back down, they release light in shimmering greens, reds, and purples. The sky seems to breathe color, but the cause is grounded in plasma physics, magnetism, and atmospheric chemistry. Even on Earth, humans use plasma as a tool. Plasma cutters can slice through metal by using an electrically conductive jet of hot plasma. Fluorescent lamps and neon signs use electrical discharges through gas to create glowing light, though the colors depend on the gas and coatings involved. In medicine and manufacturing, carefully controlled plasmas can clean surfaces, modify materials, sterilize instruments, or help produce computer chips. Plasma is not only cosmic spectacle, it is part of technology, industry, and research. But it is also easy to exaggerate, so the truth needs careful edges. Not every glowing thing is plasma. Not every flame is a fully ionized plasma in the strong sense, though flames can contain charged particles and can sometimes interact with electric fields. Plasma is not energy itself. It is matter in a charged state. It is not magic fire. It is not a spiritual substance. It is physical matter whose particles have been separated into charges enough for electromagnetic behavior to dominate. This is what makes it so powerful and so strange. It carries matter into a state where invisible fields become visible through motion and light. And perhaps the most astonishing fact is that plasma may be the most common ordinary matter state in the visible universe, because stars are made of it, and stars dominate what we see across cosmic distances. On Earth, solids and liquids feel normal because we live on a cool, rocky planet with oceans, air, and bodies built for moderate temperatures. But across the universe, much of the shining matter is plasma. Our sense of what is normal is local. We call solid ground ordinary because we stand on it. We call liquid water ordinary because we drink it. We call gas ordinary because we breathe it. But the cosmos, seen through stars, nebulae, and ionized clouds, tells another story. Matter often glows, flows, and responds to magnetism in ways that would seem impossible if Earth were your only classroom. Plasma can also be difficult to contain, and this is one reason fusion energy is so challenging. To make fusion happen on Earth, scientists try to create and control extremely hot plasma, because atomic nuclei need enough energy to overcome their natural repulsion and fuse. No ordinary container can simply hold such a plasma by touching it. It would cool, damage the walls, or lose stability. So researchers use magnetic fields in devices such as tokamaks and stellarators, trying to confine plasma without letting it touch the surrounding material directly. The dream is to reproduce, in a controlled way, part of what stars do naturally: release energy by fusing light elements into heavier ones. Progress is real, but the engineering is extraordinarily hard. Plasma does not sit still politely. It can develop instabilities, turbulence, leaks, and patterns that must be understood and controlled. This is another reminder that plasma is not only a state of matter, it is a dynamic world of behavior. It can be shaped, but it also pushes back with complexity. There is something deeply humbling in that. A substance can become so responsive to fields, so full of motion and charge, that it turns matter into a kind of visible storm. It glows not because it is pretending to be alive, but because particles are being excited, separated, accelerated, and recombined. It moves along magnetic lines not because it sees them, but because charged particles feel forces that your eyes cannot. It fills stars, flashes in lightning, dances in auroras, powers certain lamps, cuts metal, and may one day help power cities through fusion. Plasma is what happens when matter becomes energetic enough to reveal another layer of its personality. It is not solid because it does not keep a fixed shape. It is not liquid because it does not simply flow with a surface. It is not ordinary gas because its charges make it electrically active and magnetically responsive. It is matter awake to fields. So the next time you see lightning split the sky, or a neon sign glow in a dark street, or a video of the sun lifting vast loops of fire-colored material into space, remember that you are not only seeing brightness, you are seeing matter in a charged state, matter loosened from neutrality, matter behaving as a collective instead of a crowd of isolated particles. And maybe that is why plasma feels so otherworldly even when it is real. It shows that the familiar categories were never the whole story. The universe has more than one way for matter to exist, and sometimes, under enough energy, matter stops merely occupying space and begins to shine, conduct, twist, and answer the invisible architecture of fields. Graphene is one atom, thick but extremely strong. A material can be so thin that it is almost impossible to imagine, yet so strong that it changed the way scientists think about what matter can do. Graphene is only one atom thick, not one hair thin, not one layer of paint thin, not even one microscopic sheet in the usual sense, but a single layer of carbon atoms arranged in a flat honeycomb pattern. If you could shrink yourself down and look across it, you would not see a thick wall or a stacked surface. You would see carbon atoms connected in a repeating network, each one bonded to its neighbors in a way that gives the sheet extraordinary strength. This is what makes graphene feel almost unreal. It is barely there, and yet it is not fragile in the way barely there usually means. In its perfect form, graphene is one of the strongest materials ever measured, especially when you compare strength to thickness and weight. But the truth is more careful than the headline. Graphene is incredibly strong as a flawless single sheet. Yet real graphene samples can have defects, cracks, grain boundaries, wrinkles, or contamination that reduce performance. A tiny tear can spread. A large manufactured sheet is not automatically as perfect as a small laboratory sample. So graphene is not magic paper that can never break. It is a material whose atomic structure gives it astonishing potential, while the real world still asks hard questions about how to make it cleanly, cheaply, and at scale. To understand why it is so special, you first have to understand carbon. Carbon is one of nature's great shapeshifters. The same element can become diamond, where atoms form a rigid three-dimensional network. Graphite, where atoms form stacked layers that slide over one another. Or graphene, where a single layer is separated from the stack. In graphite, the layers are weakly held together, which is why pencil lead can leave marks on paper. When you write with a pencil, tiny layers of graphite slide off and stay behind. Graphene is essentially one of those layers isolated on its own, a single carbon sheet. For a long time, some scientists doubted that such a two-dimensional material could exist freely and remain stable, because heat and motion might be expected to distort it. But graphene was experimentally isolated in the early 21st century, famously using a surprisingly simple method: peeling layers from graphite with adhesive tape until extremely thin flakes remained. That humble method opened the door to a new world. It showed that a material almost unimaginably thin could be studied, touched by instruments, and used to explore physics in a fresh way. The strength of graphene comes from the strong bonds between carbon atoms in the sheet. These bonds form a stable network that resists being pulled apart. But strength is only one part of the story. Graphene also conducts electricity extremely well, because electrons can move through its structure with unusual ease. It conducts heat very efficiently too, spreading thermal energy across the sheet. It is nearly transparent because it is so thin, yet it still absorbs a small amount of light. It is flexible, lightweight, and, in many conditions, surprisingly impermeable to gases, meaning even tiny atoms can struggle to pass through a perfect graphene layer. Think about that for a moment. A sheet one atom thick can act as a barrier. It can be almost invisible, yet still block. It can bend, yet remain strong. It can conduct, yet weigh almost nothing. This combination of properties is why graphene created so much excitement. Scientists imagined ultralight composites, flexible electronics, sensitive detectors, better batteries, water filtration membranes, transparent conductors, stronger materials, faster devices, and new kinds of sensors. Some of these possibilities are real areas of research, and some are already finding limited practical uses, especially when graphene or graphene-like materials are added to composites, coatings, inks, sensors, and specialized devices. But again, honesty matters. Graphene has not transformed everyday life overnight. There are reasons. Making large amounts of high-quality graphene with the right size, purity, structure, and cost is difficult. Different production methods create different kinds of graphene, and not all of them have the same properties. A tiny, perfect flake in a lab is different from a powder mixed into plastic, and both are different from a large single crystal sheet grown for electronics. The word graphene can sometimes be used loosely in marketing, even when the material is actually a mixture of few-layer flakes, oxidized sheets, or other carbon forms. This is why the real science is more interesting than the hype. The material is extraordinary, but it is not automatically a solution to every problem. For electronics, for example, graphene conducts beautifully, but it does not naturally behave like silicon in the exact way needed for many digital switches because it lacks a natural band gap. That makes it difficult to simply replace silicon in computer chips. Researchers can engineer graphene or combine it with other materials, but each solution brings trade-offs. In water filtration, graphene-based membranes may offer powerful possibilities, but building durable, scalable, selective membranes is a serious engineering challenge. In batteries, graphene can improve certain properties, but it does not magically multiply energy storage beyond physical limits. The promise is real, but the pathway is complex. And perhaps that complexity is part of what makes graphene such a perfect symbol of modern materials science. It reminds you that discovery is not the same as instant revolution. Nature can hand us a material with astonishing properties, and then we must learn how to manufacture it, control it, integrate it, test it, and understand its limits. The wonder does not vanish because the work is hard. The wonder becomes deeper because the material is real enough to resist easy fantasy. At the atomic level, graphene also changed how scientists explore electrons moving through a flat structure. Inside graphene, electrons can behave in unusual ways, that make the material a playground for physics. Researchers study how its properties change when stacked, twisted, stretched, cut into ribbons, placed on other surfaces, or combined with other two-dimensional materials. In recent years, entire families of atomically thin materials have become important, including boron nitride, transition metal dichalcogenides, and layered structures where different sheets are stacked like pages in a book made of atoms. Graphene helped open that imagination. If one layer can be isolated, studied, and used, then perhaps matter can be designed layer by layer, with each sheet contributing a different ability. One layer conducts, another insulates, another interacts strongly with light, another has useful magnetic or electronic behavior. The future of materials may not only be about discovering substances in bulk, but about arranging thin layers with almost architectural precision. This is where graphene becomes more than a strong sheet. It becomes a doorway into a new way of building matter. Instead of carving objects from large pieces, scientists can think about assembling function from atomic layers. And this changes the emotional meaning of thinness. In everyday life, thin things feel weak. A thin thread snaps, a thin sheet tears, a thin wall fails. But graphene teaches that thinness does not always mean weakness. At the atomic level, strength comes from bonding, structure, and order. A single layer can be powerful if its internal connections are strong enough. A material can appear almost absent and still carry extraordinary ability. There is something quietly philosophical in that, but the science stands on its own. Graphene is strong because of carbon-carbon bonds arranged in a precise two-dimensional lattice. It is conductive because of how electrons move through that lattice. It is transparent because it is only one atom thick. It is difficult to perfect because reality at scale is messy. Defects matter, edges matter, contamination matters, production matters. The smallest imperfections can decide whether the dream becomes a device or remains a laboratory image. So the next time you hear that graphene is one atom thick and extremely strong, do not imagine an indestructible miracle sheet floating outside physics. Imagine something more grounded and more astonishing. A single layer of carbon atoms, almost weightless, almost transparent, held together by some of the strongest bonds in chemistry, revealing that matter does not need thickness to have power. Imagine a pencil's hidden layer becoming a scientific revolution. Imagine the ordinary element carbon, already present in your body, in trees, in charcoal, in diamonds, rearranged into a form that lets electrons race, heat spread, gases stop, and engineers dream. Graphene is not proof that the future will be easy. It is proof that the familiar world still contains arrangements we barely understand how to use. Sometimes the strongest things are not massive. Sometimes they are precise. Sometimes reality hides its most surprising abilities, not in what is large and heavy, but in a sheet so thin it is almost only a surface, and yet strong enough to remind us that the architecture of atoms can turn near nothing into something extraordinary. Lightning can be hotter than the surface of the sun. For a fraction of a second, the sky can draw a line so hot that it outshines your instincts about fire. Lightning looks like brightness first, like a sudden white crack across the clouds. But what you are really seeing is air being forced into an extreme state by electricity. In ordinary life, air feels empty and passive. It surrounds you quietly, moves as wind, fills your lungs, carries sound, and disappears from attention unless it becomes cold, hot, smoky, or stormy. But during a lightning strike, that familiar air is violently transformed. A huge electrical difference builds between clouds, or between a cloud and the ground, until the insulating ability of air breaks down. Air normally resists the flow of electricity, but under a strong enough electric field, some electrons are torn loose from atoms and molecules, creating a conductive path. Then a powerful current surges through that path, and the air in the channel heats almost instantly. The temperature inside a lightning channel can reach around 30,000 Kelvin, which is several times hotter than the visible surface of the sun, called the photosphere. The sun's surface is roughly 5,500 degrees Celsius. while the lightning channel can be far hotter for an incredibly brief moment. But this comparison needs careful honesty because it is easy to misunderstand. Lightning is hotter than the surface of the sun, not hotter than the sun's core. The core of the sun is vastly hotter, reaching millions of degrees, where nuclear fusion occurs under crushing pressure. Lightning is also not hotter in the sense of containing more total energy than the sun's surface across any large area. Temperature and total heat are not the same thing. A tiny spark can have a very high temperature but contain little total energy compared with a large warm object. Lightning's channel is narrow, temporary, and explosive. The sun is enormous, sustained, and continuously radiating immense power. So the true wonder is not that lightning defeats the sun, but that a thread of air on Earth can briefly reach temperatures far beyond the surface of a star. That alone is astonishing enough. The reason lightning becomes so hot is that electrical energy is dumped into a very thin path very quickly. The air molecules do not have time to gently warm. They are shocked into violent motion. Temperature, at its simplest, is connected to how intensely particles are moving. This sudden expansion is what creates thunder. The bright flash and the sound are part of the same event, but light reaches you almost instantly, while sound travels much more slowly through air. That is why you see lightning before you hear thunder, and why counting the seconds between them can help estimate how far away the strike was. The thunder is not the clouds colliding. It is not the sound of electricity itself in some mystical sense. It is the shock wave produced when superheated air expands and then collapses outward into surrounding cooler air. A close thunderclap cracks sharply because the pressure wave reaches you with power. A distant thunder roll lasts longer because sound from different parts of the lightning channel arrives at slightly different times, stretched and softened by distance, landscape, and atmosphere. The bolt you see is not always one simple line either. Before the main bright flash, faint branching paths called step leaders can move down from the cloud in jumps, searching for a route through the air. From the ground or tall objects, upward streamers may rise to meet them. When a connection forms, a powerful return stroke races upward along the path, producing the brilliant flash your eye recognizes as lightning. The name return stroke can be confusing because it appears to the observer as light along the channel, but the process involves charge moving and the electric field rearranging along the newly opened path. A single visible flash may contain several strokes, which is why lightning can flicker. What looks like one event can be a rapid sequence of electrical surges along the same or nearby channels. This complexity explains why lightning has such jagged shapes. It is not drawing randomly for beauty. It is following paths of least resistance through air that is constantly changing in moisture, temperature, pressure, charge distribution, and microscopic conditions. The bolt branches because the electrical breakdown explores many possible channels before one becomes dominant. The sky becomes a temporary map of electrical tension, and when the channel forms, air does something dramatic. It becomes luminous because its atoms and molecules are excited by the energy and release light as they return to lower states. That light can appear white, blue-white, violet, or sometimes tinted by rain, dust, distance, or the camera capturing it. The color is not only one simple temperature reading. It also depends on atmospheric conditions and the way your eyes or sensors receive the flash. Lightning can occur inside clouds, between clouds, from cloud to ground, from ground to cloud, and even upward from tall structures into storm systems. Most lightning does not strike people or buildings. Much of it stays within clouds. But cloud-to-ground lightning is the kind that most directly reminds us that the atmosphere is not just scenery. It is an electrical environment. Storm clouds separate charge through complicated processes involving ice particles, graupel, water droplets, collisions, and rising and sinking air currents. Scientists continue to study the exact details, but the broad result is clear. Regions of charge build up, electric fields strengthen, and when the conditions allow, the air breaks down and lightning forms. This makes a storm cloud feel less like a grey object floating overhead and more like a giant electrical machine assembled from moisture, cold, turbulence, and height. It is not alive. but it is active in a way that can feel almost intentional. Yet lightning's violence is also brief. The channel forms, burns with extreme heat, expands the air into thunder, and disappears. The air cools, the sky closes. What remains may be a smell, a memory, a scar on a tree, a damaged power line, a fire, or a strange glassy formation called fulgurite if lightning strikes sand or soil and melts material along its path. Fulgurites are natural records of lightning's heat, fragile tubes or branching shapes left behind when the ground briefly becomes hot enough to fuse. They are like fossilized lightning, not in the sense of preserving the bolt itself, but in preserving the path where energy entered the earth. Lightning can also affect atmospheric chemistry. Its extreme heat allows nitrogen and oxygen in the air to react, forming nitrogen oxides, which can later contribute to compounds that enter soil through rain. This is one small part of how storms participate in the planet's chemical cycles, though most nitrogen fixation on Earth comes from biological processes and human activity. Still, it is striking to realize that lightning is not only spectacle. It changes air. It starts fires. It shapes ecosystems. It influences chemistry. It reveals the atmosphere as a place where energy can suddenly reorganize matter. This is why the comparison to the sun's surface is so powerful when handled correctly. The sun is the steady furnace of our days, a star whose surface pours light across the solar system. Lightning is a local atmospheric discharge, a temporary event born from storm conditions. They are not equal things, but for one narrow instant, the air in a lightning channel can reach a temperature higher than the surface we see when we look at the sun. That fact forces the mind to separate scale from intensity. The largest thing is not always the hottest in every part. The brightest presence in the sky is not the only place where extreme temperatures appear. Nature can concentrate energy into a tiny path and briefly create conditions that feel impossible beside everyday weather. A raindrop may fall cold on your skin while somewhere inside the same storm, air is being heated to star surface-defying temperatures. That contrast is what makes lightning so unforgettable. It belongs to weather, but it behaves like a glimpse of cosmic violence brought down into the atmosphere. It is born from clouds, but it speaks in temperatures that belong to stars. And still, its danger is not symbolic. Lightning can kill, burn, stop the heart, damage nerves, ignite fires, and travel through ground, metal, plumbing, and electrical systems. The beautiful fact should never soften the practical one. If you can hear thunder, you are close enough to be at risk, and shelter matters. Science does not make lightning safer by making it understandable. It makes your respect more precise. You stop seeing the bolt as just a dramatic flash and start seeing it as a sudden conducting channel, an extreme heating event, a shockwave generator, a chemical trigger, and a reminder that the air above you can become dangerous under the right conditions. So the next time a storm rolls in and the sky lights up for one breathless instant, remember what you are witnessing. Not just brightness, not just noise, not just weather. You are seeing air torn open by electricity, heated to a temperature higher than the sun's visible surface, expanded so violently that the atmosphere itself cracks into sound. You are watching the familiar sky reveal a hidden ferocity, proving that even the space you walk through and breathe can, under enough tension, become a blazing path for power. And maybe that is why lightning holds the human imagination so tightly. It is both near and unreachable, ordinary and extreme, a storm-born reminder that the world above your head is not empty calm, but a charged ocean waiting sometimes to write its energy across the dark. Your blood carries elements made inside ancient stars. Inside every drop of your blood, there is a piece of an ancient star doing quiet work for your next breath. That may sound poetic, but it is also one of the most grounded truths in science. Your blood is not just red liquid moving through veins. It is a living transport system carrying oxygen, nutrients, immune cells, chemical messages, waste products, and heat through the private rivers of your body. And at the center of its most famous task, carrying oxygen, there is iron. Iron sits inside hemoglobin, the protein in red blood cells that binds oxygen in your lungs and releases it into tissues that need it. Without that iron, your body could not move oxygen efficiently enough to support the life you know. Your thoughts, your muscles, your heartbeat, your warmth, your ability to climb stairs, speak, heal, and stay awake all depend on red blood cells moving oxygen from breath to body. But the iron doing that work was not made inside your body. It was not created by Earth. It was forged long before you existed, in the violent histories of stars. In the early universe, the simplest elements formed first, mainly hydrogen and helium, with a little lithium. The heavier ingredients needed for rocky planets, oceans, bones, and blood came later. Through the lives and deaths of stars, stars are not only lights in the sky. They are cosmic furnaces, places where pressure and temperature allow lighter atomic nuclei to fuse into heavier ones. For much of a star's life, fusion creates energy that helps hold the star up against gravity. In massive stars, as fuel changes and the core grows more complex, fusion can build elements in layers, like a hidden structure of fire inside the star. But iron is special. Fusing iron does not release energy in the way earlier fusion steps do. For a massive star, building up to iron in the core is like reaching the end of a road. Once the core can no longer support itself through energy-producing fusion, gravity wins with terrifying speed. The core collapses, outer layers fall inward and rebound, and a supernova can blast material into space. In that explosion, and in other stellar events, such as the deaths of white dwarfs in certain supernovae, huge amounts of iron and related elements are created or spread into the galaxy. Over time, those elements mix into clouds of gas and dust. Later, those enriched clouds can collapse into new stars, planets, asteroids, oceans, soils, and eventually living bodies. This means the iron in your blood is not simply a chemical ingredient. It is a survivor of cosmic recycling. It passed through stages you will never see directly. Stellar interiors, explosions, drifting interstellar clouds, the formation of the solar system, the early Earth, rocks, water, food chains, and finally your own body. When you eat iron-containing foods, such as meat, legumes, leafy greens, grains, or fortified foods, your digestive system does not know the full cosmic biography of each atom. It only handles the chemistry. It absorbs what it can, transports it, stores it, regulates it, and uses it to build hemoglobin. Your body is careful with iron because it is both essential and potentially harmful in the wrong form or amount. Too little iron can lead to anemia, leaving the body short of healthy oxygen-carrying capacity. Too much free iron can contribute to damaging chemical reactions, so your body binds, stores, and moves it with proteins rather than letting it wander freely. This is one of the quiet signs of how deeply life depends on balance. The same element that helps you breathe must be managed with precision. In red blood cells, hemoglobin gives blood its red color because of how its iron-containing hem groups interact with oxygen and light. Oxygen-rich blood appears bright red, while oxygen-poor blood is darker red, not blue, despite the common myth that veins carry blue blood. Veins may look bluish through skin because of how light passes through tissue and returns to your eyes, but the blood itself remains red. This small correction matters because the real story is already beautiful enough without the myth. Your blood is red because a star-forged element is held inside a protein built by your cells, and that element helps carry the oxygen your mitochondria use to release energy from food. Every breath becomes chemistry. Every heartbeat becomes delivery. Every red blood cell becomes a tiny courier, carrying a star-made tool through the dark tunnels of your body. Red blood cells themselves are remarkable. They are shaped like flexible discs, allowing them to squeeze through narrow capillaries. Mature human red blood cells do not have a nucleus, giving them more room for hemoglobin. They live for about 4 months before being removed and recycled mainly by the spleen and liver. Your body then salvages much of the iron and uses it again. So even inside you, iron is not wasted casually. It circulates, returns, and re-enters the work of life. In a way, your body repeats the larger universe on a smaller scale. Matter is transformed, reused, and passed onward. But the cosmic origin remains the most humbling part. You are not separate from astronomy. You are not merely looking at the stars from below. Some of the matter inside you comes from stars that lived and died before the sun was born. The iron in your blood may have been scattered across space by explosions that happened billions of years ago, long before Earth had oceans, long before life had eyes, long before any creature could look upward and wonder where it came from. And now that same iron sits inside hemoglobin, helping oxygen attach, release, and sustain the fragile warmth of consciousness. This does not mean every atom in your body was made in the same kind of star or the same event. Different elements have different origins. Hydrogen in your body mostly traces back to the early universe. Carbon, oxygen, nitrogen, calcium, and other elements have histories tied to different stellar processes. Some heavy elements are built in neutron star mergers or rare explosive events. The body is not made from one cosmic source, but from many. It is a gathered history, a temporary arrangement of ancient materials. Blood makes that history feel intimate because it moves. You can hear its pulse in your ears after running. You can see it bead from a cut. You can feel your heart push it through you, rhythm after rhythm, without asking your permission. And within that movement is matter older than the planet beneath your feet. The thought can feel almost too large for the body to hold. A star dies, a galaxy mixes its ashes, a solar system forms. Earth cools, life evolves, animals breathe, humans appear. And one day you sit quietly with a pulse in your wrist, carrying iron from ancient stellar death as if it were the most ordinary thing in the world. Maybe that is what makes this truth so powerful. It does not make you larger in an arrogant way. It makes you more connected in a humble one. You are not made of special materials separate from the universe. You are made from the universe's old work. Your blood is not alien to the stars. It is one of the ways their history continues. Every inhale brings oxygen into your lungs. Every red blood cell receives it, carries it, releases it. Every moment of awareness depends on this delivery. And beneath that simple act is a cosmic chain so long that the mind can barely follow it. So the next time you feel your heartbeat in the quiet, do not think of it as only a biological rhythm. Think of it as ancient matter being used for present life. Think of iron forged in stellar fire now helping you read, listen, move, heal, and wonder. The stars are not only above you. Some of their remains are inside the red river that keeps you alive, traveling through you in silence, proving that the distance between the cosmos and the body was never as great as it seemed. Your body is home to trillions of microbes. You are not walking through the world as one life, but as a moving habitat filled with countless smaller lives. On your skin, in your mouth, along your gut, inside the folds and surfaces your eyes never see. There are bacteria, fungi, viruses, archaea, and other microscopic companions living in communities so complex that your body is less like a sealed machine and more like a planet with climates, neighborhoods, borders, and ecosystems. The phrase, "your body is home to trillions of microbes," sounds strange because you are used to thinking of yourself as a single person with one face, one name, one memory, one private sense of me. But biologically, you are also a host. You are an environment. You are a warm, moving world where microscopic life has been living, changing, competing, cooperating, and adapting since the beginning of your life. This does not mean you are dirty. It does not mean you are infected. It does not mean microbes are enemies hiding inside you. Many of them are part of normal human biology. Some help digest components of food your own enzymes cannot fully break down. Some produce useful molecules. Some help train your immune system to recognize danger without attacking everything. Some occupy space that could otherwise be taken by harmful invaders. Your body is not sterile, and it is not supposed to be. In fact, complete sterility would be dangerous for a living human. Life on Earth did not evolve in isolation from microbes. It evolved among them, with them, and often through them. Your gut microbiome, especially in the large intestine, is one of the richest microbial ecosystems in the body. There, microbes feed on fibers and other compounds that reach them after digestion. In return, Some produce short-chain fatty acids, molecules that can support the cells lining the gut and influence metabolism and immune activity. This is one reason diet matters beyond calories. When you eat plants, fibers, fermented foods, or varied whole foods, you are not only feeding yourself in the simple sense, you are also changing the resources available to your microbial communities. Different microbes thrive on different materials. A long-term diet can help shape which groups become more common, which functions become stronger, and how stable the ecosystem remains. But the truth must stay careful. There is no single perfect microbiome that every person should have. A healthy microbiome can look different from person to person. It varies with genetics, age, diet, environment, medications, geography, pets, birth history, hygiene, stress, illness, and many other factors. Two healthy people may carry different microbial communities and still function well. This is why simple claims like "this one supplement fixes your microbiome" should be treated with caution. The microbiome is not a button you press. It is a living system with context. Antibiotics show how delicate and powerful this system can be. These medicines can be life-saving when used properly against bacterial infections, but they can also disrupt normal microbial communities because they do not always distinguish neatly between harmful bacteria and helpful or harmless ones. After antibiotics, some microbial populations may recover, some may take longer, and some changes can create opportunities for unwanted organisms to grow. This does not mean antibiotics are bad. It means they are powerful and should be used responsibly. The same lesson applies more broadly. Your microbes are part of your biology, so disturbing them can matter, but protecting them does not require fear of every surface or rejection of modern medicine. Your relationship with microbes is not a fairy tale of pure harmony. It is a balance. Some microbes are helpful in one place and harmful in another. A bacterium that lives peacefully on the skin may cause trouble if it enters the bloodstream through a wound. A microbe that is harmless in one person may be risky for someone with a weakened immune system. Even within the gut, balance matters. Too much growth of certain organisms, loss of diversity in certain contexts, or changes after illness can be associated with health problems. But association is not always causation. Scientists are still working to understand when microbes drive disease, when they respond to disease, and when both are shaped by deeper conditions. This is one of the most exciting and difficult frontiers in biology, learning how to read a living ecosystem inside the body without reducing it to simple slogans. Your skin has its own microbiome too, and it is not the same everywhere. The oily areas of your face, the moist areas under arms, the dry surfaces of your forearm, the spaces between toes, each can support different microbial communities. Your skin is not just a covering, it is a border ecosystem, exposed to air, touch, washing, clothing, sunlight, sweat, oil, wounds, and temperature changes. Microbes living there can interact with the immune system and with each other, sometimes helping defend territory, sometimes contributing to odor, irritation, or disease when balance shifts. Your mouth is another world, with microbes living on the tongue, teeth, gums, and saliva. Dental plaque is not simply dirt, but a biofilm, a structured microbial community attached to surfaces. Some oral bacteria contribute to cavities by producing acids from sugars, which can damage tooth enamel over time. Others are part of normal oral ecology. The mouth is a reminder that microbes do not merely float randomly. They build communities, attach, communicate chemically, compete, cooperate, and change their behavior depending on the environment. A biofilm can be more resistant and organized than isolated microbes. That is why brushing, flossing, saliva, diet, and dental care matter. You are not just cleaning a surface, you are managing a microscopic city. Even viruses are part of the story. The human microbiome includes bacteriophages, viruses that infect bacteria, and they can influence which bacterial populations thrive or decline. Fungi also live in and on the body in smaller numbers, sometimes peacefully, sometimes causing problems under certain conditions. The human body is not ruled by one kind of microbe. It is a crowded, changing network of many forms of life, interacting at scales too small for your senses. And perhaps the most humbling part is that your immune system does not simply attack microbes blindly. It learns, it negotiates. It tolerates some organisms while responding fiercely to others. From early life, exposure to microbes helps educate immune responses. Birth, breastfeeding, environment, family contact, and later diet and lifestyle all help shape the developing microbiome and immune system. This does not mean every exposure is good or that harmful infections should be welcomed. It means the immune system grows within a microbial world, not outside it. Cleanliness protects us from disease, but the fantasy of a completely microbe-free life misunderstands what a human being is. You are not an isolated fortress. You are a controlled border, a managed ecosystem, a collaboration with limits. The microbes inside and on you do not think of you as you. To them, your body is temperature, moisture, nutrients, oxygen levels, acidity, surfaces, and chemical signals. Your breakfast may be a weather change. Your medicine may be a disaster or a rescue. Your sleep patterns, stress hormones, and immune activity may shift the landscape. And in return, their activity can influence digestion, chemical production, inflammation, and possibly even signals connected to the nervous system. Though many brain microbiome claims are still being studied and should not be exaggerated, the gut and brain do communicate through nerves, immune signals, hormones, and metabolites. But it is too simple to say your microbes control your mood. The truth is more subtle. They are part of a larger body-wide conversation. They may influence conditions that affect how you feel, but they do not replace your brain, your experiences, your environment, or your choices. This careful version is more powerful because it is real. It shows that being human is not a solo performance. It is a layered biological event. Your cells and microbial cells share space. Your immune system monitors boundaries. Your gut feeds both you and your microbial partners. Your skin hosts life while protecting you from the world. Your mouth carries communities that can help or harm depending on care and context. You are not just made of human cells acting alone. You are a living arrangement where countless small organisms participate in the conditions of your health. And this should not make you feel invaded. It should make you feel more connected to life itself. The line between you and the world has always been more porous than it seemed. Every breath, meal, touch, and place you live helps shape the microscopic ecology you carry. You are partly a record of your environment, a city, a diet, a childhood home, a pet, a medicine, a garden, a hospital, a family table. All can leave invisible traces in the communities that live with you. So the next time you think of your body as one object moving through space, remember that it is also an inhabited landscape. Beneath the simplicity of your reflection is a hidden biosphere, not separate from you, not identical to you, but woven into the way you digest, defend, adapt, and live. You are not alone in your own skin, and you never have been. You are a human being, yes, but also a host, a habitat, a walking ecosystem whose quiet passengers remind you that life is not only something you possess, it is something you share. Your bones are alive and constantly rebuilding. Your skeleton is not a dry frame hidden under your skin. It is a living construction site that never fully closes. It is easy to imagine bones as pale, hard, finished things, like stones shaped into the outline of a body, useful only because they hold you upright and protect the softer organs inside. But that picture is too still. Bone is not dead architecture. Bone is active tissue filled with cells, blood vessels, nerves, minerals, marrow, and constant communication. Every day, your bones are being repaired, reshaped, strengthened, weakened, scanned, and renewed in microscopic regions you never feel. The skeleton you carry is not the exact same skeleton you carried years ago in every detail. Its material is continuously remodeled, not all at once. Not like replacing a whole building overnight, but like a city repairing roads. Removing old bricks, reinforcing stressed bridges, and quietly redesigning itself while people keep living inside it. This process is called bone remodeling, and it depends on a careful balance between cells that break down old bone and cells that build new bone. Osteoclasts remove bone tissue by dissolving mineral and breaking down the hardened matrix. Osteoblasts follow by laying down new bone material, which later becomes mineralized and strong. Another kind of bone cell, the osteocyte, lives embedded inside the bone itself and acts like a sensor, helping detect strain, damage, and mechanical pressure. These cells are not random workers. They are part of a responsive system. When bone experiences repeated load, such as walking, lifting, running, climbing, or resisting gravity through normal movement, it can adapt by becoming stronger in the areas that need support. When bone is not used enough, such as during long bed rest or in the weightlessness of space, it can lose density because the body no longer receives the same signals that strong bone is needed there. This is one reason astronauts must exercise intensely in orbit and why long inactivity can weaken the skeleton. Bone listens to use. It does not listen with ears, but with cellular sensors that translate pressure and bending into biological instructions. That idea alone changes the way you think about your body. Your skeleton is not simply something you own. It is something your life is constantly instructing. Every step is a message. Every load is information. Every period of stillness has meaning. The body is always asking, what world are we living in, and how much strength do we need for it? But bone remodeling is not only about movement. It is also deeply tied to chemistry. Bones store minerals, especially calcium and phosphate, which give them hardness and help many body systems function. Calcium is needed for muscles to contract, nerves to signal, blood to clot, and cells to communicate. Because calcium is so important in the bloodstream, the body regulates it carefully with hormones such as parathyroid hormone, calcitonin, and vitamin D-related pathways. If blood calcium needs adjustment, bone can become part of that regulation, releasing or storing mineral depending on the body's needs. This does not mean bones are just mineral warehouses. They are both structure and chemistry, both support and reserve, both protection and participation. Their strength comes from a combination of hard mineral crystals and flexible collagen fibers. Mineral gives bone its firmness. Collagen gives it toughness and helps resist cracking. If bone were only mineral, it would be brittle like chalk. If it were only collagen, it would be too soft to support you. Bone works because it is a composite material, a natural partnership between stiffness and flexibility. This is why it can absorb stress, heal after fractures, and maintain shape under daily force. When a bone breaks, the body does not simply glue it back together like a broken cup. It launches a healing process. Blood clots form around the fracture. Inflammatory signals call cells to the area. A soft repair tissue begins to bridge the gap, then gradually hardens into new bone. Over time, remodeling reshapes the repaired region so it becomes stronger and more organized. This can take weeks, months, or longer, depending on the bone, the person, the injury, and the conditions for healing. The process is one of the clearest proofs that bone is alive. A stone cannot heal itself. A plastic rod cannot sense damage and rebuild with living cells. Your bones can, because they are vascular, cellular, and biologically active. Inside many bones, marrow also carries out essential work. Red marrow produces blood cells, including red blood cells, white blood cells, and platelets. Yellow marrow stores fat and can change under certain conditions. So the skeleton is not only a frame around life, it is one of the places where life is produced. Hidden inside the hardness is a factory of renewal. That is a strange contrast. The solid parts of you contain some of the most active sources of new cells. Your skull protects the brain. Your ribs guard the lungs and heart. Your spine supports posture and houses the spinal cord. Your pelvis carries weight and anchors movement. But inside this architecture, biological work continues in silence. Bone is also shaped by age. In childhood and adolescence, bone formation outpaces breakdown, allowing growth and increasing bone mass. In early adulthood, bone mass usually reaches a peak. Later, remodeling continues, but the balance can shift. If breakdown begins to exceed formation over time, bones can become less dense and more fragile, a condition that can contribute to osteoporosis. This is especially important with aging and hormonal changes. But bone health is influenced by many factors, including nutrition, physical activity, sunlight and vitamin D status, genetics, illness, medications, and lifestyle. The honest lesson is not that bones are unbreakable if you simply use them, or that every weakness is someone's fault. Biology is more complex than that, but it is true that bones respond to the conditions of a life. They are shaped by movement, minerals, hormones, repair, and time. Even their appearance carries history. A tennis player may develop stronger bone in the arm used most often. A person's skeleton can reflect patterns of activity, injury, growth, and stress. Archaeologists and forensic scientists can sometimes read bones for clues about diet, disease, labor, age, trauma, and the physical demands of past lives. Bone remembers in structure, not in thought. It records pressure in thickness, healing in scars, age in density, and use in architecture. This makes the skeleton feel less like an object and more like a biography written in mineral and collagen. And yet, for all this activity, you rarely notice it. You do not feel osteoclasts clearing microscopic areas. You do not feel osteoblasts laying down new matrix. You do not feel calcium being managed moment by moment. You simply stand up, walk, reach, sleep, wake, and trust the hidden frame. The quietness of bone is part of its mystery. It works best when you do not have to think about it. But learning what it is doing beneath awareness can make ordinary movement feel different. A step is not just a step. It is a signal to living tissue. A healed fracture is not just a fixed injury. It is evidence of a body that can rebuild its own support beams. A child growing taller is not simply stretching upward. Their bones are lengthening at growth plates through coordinated cellular activity. An elderly person protecting bone strength is not only preserving hardness, they are preserving independence, balance, mobility, and the ability to keep meeting the world upright. The skeleton is where physics and biology shake hands. It must obey gravity, resist impact, transmit muscle force, protect delicate organs, store minerals, and renew itself without collapsing the body it supports. It is engineering made alive. So the next time you think of bones as something silent and dead, remember that the silence is misleading. Beneath your skin, your skeleton is being rewritten in slow, careful edits. Old material is removed, new material is placed. Tiny damage is repaired before it becomes catastrophe. Marrow produces cells. Minerals are stored and released. Shape follows use. Strength follows demand. Time leaves traces. Your bones are not relics inside you. They are living records of motion, pressure, nourishment, healing, and age. And maybe that is the quiet wonder of the skeleton. It holds you up not by being unchanged, but by changing just enough to keep holding you. Your brain has no pain receptors of its own. The organ that creates every pain you have ever felt cannot feel pain in its own tissue. That sounds almost impossible, because the brain is where pain becomes experience. A burned finger, a twisted ankle, a headache, a deep ache in the stomach, the sting of a cut, the pressure of a bruise. None of these become pain until signals travel through nerves, enter the spinal cord, reach the brain, and are shaped into awareness. The brain is the place where the warning becomes personal. It gives pain a location, intensity, meaning, memory, and emotional weight. And yet the brain tissue itself has no pain receptors of its own. If the brain could somehow be touched directly under the right medical conditions, the grey and white matter would not hurt the way skin hurts. Because the brain does not contain the same kind of nociceptors, the specialized nerve endings that detect harmful pressure, heat, chemical irritation, or injury in many other parts of the body. This is one reason awake brain surgery is possible. In certain operations, surgeons can keep a patient awake while working on the brain, often to map speech, movement, or other important functions, and avoid damaging critical areas. The patient's scalp and skull must be carefully numbed, because those tissues can feel pain. The membranes around the brain, called the meninges, and the blood vessels in and around the brain, can also be pain sensitive. But the brain tissue itself can be stimulated without producing the direct pain you might expect. Sometimes stimulation may cause movement, tingling, memories, speech changes, flashes, or other strange experiences depending on the region involved, but not ordinary pain from the brain tissue being touched. That fact reveals something subtle and profound. Pain is not simply located where it feels like it is located. Pain is constructed by the nervous system from signals, context, attention, expectation, memory, and threat detection. Your finger does not contain pain like water in a cup. Your finger contains sensors that send warnings. The brain reads those warnings and creates the experience that makes you pull away, protect the injury, learn from the danger, and survive. Pain is not a flaw in the body. It is a protective language. It is unpleasant because it is supposed to be difficult to ignore. A body that could not feel pain would be in constant danger because damage could happen silently. People with rare conditions that reduce or remove pain sensation can suffer serious injuries without noticing them in time. So pain, as cruel as it can feel, is often a form of protection. But the brain's own lack of pain receptors creates a strange exception. The master interpreter of pain is itself mostly silent to direct injury. This does not mean brain disease is painless or harmless. It means the pain associated with problems inside the head often comes from surrounding structures, not the brain tissue itself. Headaches, for example, are not usually the brain hurting. They can involve pain-sensitive tissues such as the meninges, blood vessels, muscles of the scalp and neck, sinuses, nerves of the face and head, or chemical and pressure changes that activate pain pathways. A migraine is not simply a bad headache caused by the brain feeling pain in its own flesh. It is a complex neurological condition involving changes in nerve signaling, blood vessel behavior, inflammation-related molecules, sensory sensitivity, and brain networks that process pain and perception. That is why migraines can bring nausea, light sensitivity, sound sensitivity, visual disturbances, and exhaustion. The pain feels as if it is inside the head because the brain maps it there. But the origin and processing are more layered than a simple sore spot. This distinction matters because it teaches you that pain is both physical and interpretive. It is not imaginary when it is constructed by the brain. Every experience you have is constructed by the brain. Vision is constructed, sound is constructed, touch is constructed. Pain is constructed too, but that does not make it fake. It makes it biological. The brain takes signals from the body and decides how threatening they are. Sometimes it amplifies pain to protect you. Sometimes it calms pain when survival requires focus. Soldiers, athletes, accident survivors, and people in emergencies may not feel injuries immediately because the nervous system can temporarily change pain processing under intense conditions. Later, when the danger passes, the pain arrives. The injury was real all along, but awareness of it changed with context. This is why pain science is so fascinating and so difficult. The same injury can hurt differently depending on stress, fear, sleep, inflammation, attention, past trauma, expectation, and the meaning the brain gives the signal. A harmless sensation can feel threatening if the brain believes danger is near. A serious wound can be muted for a short time if escape is more urgent than repair. The brain is not a passive alarm bell. It is a decision-making system trying to protect the organism, sometimes accurately, sometimes too strongly, sometimes long after the original danger has passed. Chronic pain can happen when pain pathways become sensitized, continuing to produce suffering even after tissues have healed, or when damage does not fully explain the intensity of pain. That does not mean the person is exaggerating. It means the nervous system itself has changed. The brain and spinal cord can become better at producing pain, almost like a volume knob turned too high. Understanding this has helped medicine move beyond the old and cruel idea that pain must always match visible damage. Pain is real when it is experienced, even when its source is complex. And in the center of all this is the strange, quiet brain, unable to feel its own tissue being cut, yet able to create the agony of a paper cut, the burn of grief in the chest, the sharp warning of a toothache, the deep pressure of a migraine, the electric shock of nerve pain, and the protective ache that tells you to rest. It is like a theater that cannot watch itself from the outside, but can project every possible scene onto your awareness. The brain does not need pain receptors in its own substance because its role is not to protect itself by feeling its own surface directly. It is protected by the skull, cushioned by fluid, wrapped in membranes, supplied by blood, monitored by immune and vascular systems, and defended by the body as a whole. The tissues around it are sensitive because damage there can threaten the brain. The skull cannot swell much. The membranes can become irritated. Blood vessels can stretch or inflame. Pressure can rise, and those surrounding systems can generate severe pain. So the brain lives in a protected chamber, not numb in the larger sense, but strangely without the local pain sense that skin, muscle, joints, and organs rely on. This makes the body feel like a paradox. The thing most responsible for suffering is itself mostly painless to direct touch. But maybe that is not a contradiction. Maybe it is a clue. Pain is not a substance inside damaged tissue. It is a message created for the whole organism. It is the body speaking to the brain, and the brain speaking back to consciousness. It says, protect this, stop that, look here, something may be wrong. Sometimes it is precise, sometimes it is confused, sometimes it saves you, sometimes it traps you, but always, it is more than a simple signal traveling along a wire. It is a living interpretation. So the next time you feel pain, remember that somewhere inside your skull, an organ that cannot feel its own tissue is building the entire experience for you. It is locating danger, coloring it with fear or urgency, comparing it with memory, deciding how loudly it must speak, and hidden inside that fact is one of the strangest truths of being alive. The brain is both the silent instrument and the composer of pain, unable to hurt in itself, yet powerful enough to make the whole world ache. Your DNA is packed into microscopic space. If the DNA from just one of your nucleated cells were stretched out, it would be far longer than the cell that hides it. And yet it fits inside a space smaller than most things your eyes could ever see. That single fact sounds almost impossible because you are used to information needing room. A book needs pages, a city needs streets, a library needs shelves. But inside the nucleus of most of your cells, life stores an instruction system so long and delicate that, if simply left loose, it would be an unusable tangle. Human DNA is not a tiny dot sitting calmly inside the cell. It is a long molecule made of chemical letters arranged in sequences, carrying instructions that help cells build proteins, regulate activity, divide, repair, specialize, and respond to the body's needs. In many human cells, if you stretch the DNA end to end, it would measure roughly 2 meters, yet it is packed into a nucleus only a few millionths of a meter wide. This does not happen by random stuffing. It happens through an astonishing system of folding, wrapping, looping, and organizing. DNA is wound around proteins called histones, forming bead-like structures known as nucleosomes. These nucleosomes fold further into chromatin, a flexible and dynamic material that can be packed tightly or loosened depending on what the cell needs to access. When a cell is preparing to divide, chromatin condenses into the visible structures we call chromosomes, which help DNA separate accurately into new cells. But for most of a cell's working life, DNA is not sitting as neat X-shaped chromosomes the way textbook images often suggest. It is arranged in an organized, active, three-dimensional landscape inside the nucleus, with certain regions open for use and others kept more tightly packed. This is one of the most important truths about DNA packing. It is not only about saving space, it is also about control. A cell must not read all of its DNA at once. A nerve cell, a muscle cell, a liver cell, and a skin cell may carry largely the same genetic library, but they do not use the same sections in the same way. The difference between them is not usually that one has a completely different set of instructions, but that each cell type has learned which instructions to open, which to silence, which to repeat, and which to keep waiting. Packing helps decide accessibility. When chromatin is loose, certain genes may be easier for the cell's machinery to read. When chromatin is tightly compacted, those regions may be harder to access. Chemical tags on DNA and histone proteins can influence this organization, helping cells manage gene activity without changing the underlying sequence of letters. This is part of what scientists call epigenetic regulation, and it helps explain how the same genetic text can support many different forms of cellular identity. In other words, your DNA is not just stored, it is managed like a living archive. Some sections are brought forward, some are filed away, some are opened only under certain conditions, some stay silent for years. The nucleus is not a messy storage closet. It is more like a reading room where the arrangement of shelves affects which books can be reached at the right moment. And because DNA is so important, the packing must balance protection with access. DNA is fragile in the sense that it can be damaged by radiation, chemical reactions, copying errors, and normal metabolic stress. Yet it must also be opened and copied when cells divide and read when genes are active. Your cells constantly repair DNA damage using specialized systems. They monitor breaks, mismatches, and chemical changes, correcting many problems before they become dangerous. This repair is not perfect, and mistakes can accumulate over time, contributing to aging, cancer risk, and inherited changes when they occur in reproductive cells. But the fact that life works at all depends on the ability to pack DNA tightly while still keeping it usable. Imagine trying to store an enormous ribbon inside a tiny room, while also needing to read precise sentences from different parts of it every second, copy it without losing lines, protect it from tearing, and pass it to the next room when the time comes. That is the challenge inside your cells, and they solve it with molecular machinery so efficient that you rarely notice it unless something goes wrong. Not every cell in your body handles DNA the same way. Mature red blood cells in humans, for example, lose their nucleus as they develop, which gives them more space for hemoglobin and helps them carry oxygen efficiently. This means they no longer contain the main set of nuclear DNA. Egg and sperm cells carry half the usual number of chromosomes so that, when they combine, a full set can be restored. Mitochondria, the energy-related structures inside cells, also carry their own small amount of DNA, separate from the main nuclear genome, a clue to their ancient evolutionary history. So the story of DNA is not one simple container in one simple cell. It is a layered system, varying by cell type, life stage, and function. But in most nucleated cells, the central miracle remains. An enormous amount of genetic information is folded into microscopic space without becoming useless. The packing is so precise that some regions of the genome tend to occupy different neighborhoods within the nucleus. Genes that need to be active may be positioned and organized differently from regions that are more silent. The nucleus has no little librarian with hands, no conscious map, but it has physical organization shaped by proteins, chemical marks, loops, compartments, and molecular interactions. This organization affects development, health, disease, and identity at the cellular level. A cell is not only what genes it has, it is also how those genes are arranged, accessed, and regulated. That idea changes the emotional meaning of the genome. We often speak of DNA as if it were destiny, a fixed script locked inside us. But DNA is more like a vast text that must be interpreted by living systems. The letters matter deeply, but so does when they are read. How often, in what cell, under what conditions, and with what surrounding signals. Your body is not simply obeying DNA like a machine obeying a command. It is using DNA within a constantly changing biological conversation. Hormones, nutrients, stress, development, immune signals, environmental exposures, and random cellular events can all influence how cells behave. DNA is foundational, but it is not the whole story by itself. It is the library, not the entire city. Still, the library is breathtaking. Inside each tiny nucleus, there are instructions shaped by evolution across billions of years, inherited from parents, recombined through generations, carrying both ancient biological patterns and personal variation. Parts of your genome code for proteins. Many other parts help regulate when and where genes are used. Some regions are remnants of ancient viral insertions. Some sequences repeat. Some are still not fully understood in all their functions. The genome is not a perfectly tidy manual written for human understanding. It is more like an old living manuscript edited by mutation, selection, duplication, accident, repair, and time. And somehow, from that manuscript, cells build bodies, maintain tissues, respond to injury, and create the conditions for thought. The packing of DNA into microscopic space is therefore not just a technical problem. It is one of the ways life makes complexity possible. Without folding, the genome could not fit. Without organization, it could not be used. Without repair, it would degrade. Without regulation, every cell would lose its identity. The difference between a heart cell and a skin cell, between a growing embryo and an adult tissue, between health and certain diseases, can depend on which parts of the genetic archive are opened and which remain closed. So the next time you hear that your DNA is packed inside microscopic space, do not imagine a simple thread crushed into a tiny box. Imagine an entire molecular library folded into a room so small it disappears beneath ordinary sight, yet arranged carefully enough that a living cell can find the right passage at the right time. Imagine a 2-meter ribbon hidden in a nucleus, wrapped around proteins, looped into neighborhoods, protected by repair crews, copied during division, and interpreted differently by different cells. And maybe the deepest wonder is this: your body carries its most essential instructions not in something large and obvious, but in a molecule so thin and folded that it must be managed with impossible care. You are not only made of matter, you are made of matter that learned how to store memory in chemistry, fold it into darkness, and read it back into life. Aging is not one process, but many. Aging is not one clock inside you slowly winding down. It is a whole orchestra of small changes losing perfect timing in different parts of the body. This is why aging feels so familiar from the outside and yet becomes so difficult to explain when you look closely. Hair turns grey, skin becomes thinner, joints may stiffen, recovery takes longer, sleep changes, muscle can weaken, memory may shift, the immune system responds differently, but none of these changes come from a single switch labelled old age. There is no one master fuse that burns out and makes the body age all at once. Aging is many processes happening together, overlapping, accelerating, slowing, influencing one another, and unfolding differently from person to person. Two people can be the same age on a calendar and very different biologically. One may have stronger muscles, clearer arteries, better balance, sharper hearing, or more resilient metabolism. Another may carry more inflammation, more cellular damage, weaker repair systems, or greater disease burden. The number of years lived matters, but it does not tell the whole story. The body does not age like a phone battery simply draining in a straight line. It ages more like a city that has been running for decades. Roads crack, wiring gets patched, waste systems slow, repair crews become less efficient. Some neighborhoods remain strong, others decline faster. And the whole system depends on maintenance, environment, stress, design, luck, and history. At the cellular level, one major part of aging involves accumulated damage. Every day, cells face stress from normal metabolism, sunlight, toxins, inflammation, copying errors, and ordinary wear. The body has repair systems, but no repair system is perfect forever. Over time, damage can build up in DNA, proteins, membranes, and other cellular structures. Some proteins may misfold or clump. Some cellular machines may become less efficient. Some cells may stop dividing properly. Some tissues may lose their ability to repair as quickly as they once did. But damage alone is not the whole story. Aging also involves changes in communication. Cells are constantly sending signals to one another. Grow, rest, repair, divide, defend, stop, clean up, store energy, release energy. As the body ages, these signals can become less precise. Chronic low-level inflammation can increase, sometimes called inflammaging, where the immune system remains slightly more activated than it should be, not because of one obvious infection, but because of accumulated stress. Senescent cells, tissue damage, and altered immune regulation. Senescent cells are especially interesting. These are cells that have entered a state where they no longer divide. often as a protective response to damage or stress. In the short term, senescence can help prevent damaged cells from becoming dangerous, and it can assist in wound healing. But if senescent cells accumulate and are not cleared efficiently, they can release signals that affect nearby tissue, contributing to inflammation and decline. So the same biological process can be helpful in one context and harmful in another. That is one of the deep lessons of aging. The body is not simply failing because bad things happen. Sometimes protective systems become costly when they persist too long. Another part of aging involves the tiny power systems inside cells, the mitochondria. These structures help convert energy from food into usable cellular fuel, and they also participate in signaling, stress responses, and cell survival. As people age, mitochondrial function can change. Some cells may become less efficient at managing energy. This does not mean mitochondria are the cause of aging by themselves, but they are part of the larger network. Energy matters because repair, movement, thinking, immunity, and tissue maintenance all depend on cells having enough usable power and coordination. There is also the issue of cellular cleanup. Cells have systems for removing damaged components, recycling parts, and maintaining internal order. One of these processes is called autophagy, a kind of cellular recycling pathway. When cleanup becomes less efficient, damaged proteins or worn-out structures can accumulate, making the cell's inner environment less stable. This can matter in many tissues, including the nervous system, muscles, liver, and immune cells. Again, aging is not only about things breaking, it is also about cleanup becoming slower, communication becoming noisier, and repair becoming less complete. Outside the cell, tissues change too. The material surrounding cells, called the extracellular matrix, helps give tissues structure, elasticity, and strength. With age, this matrix can stiffen or become chemically altered. One important process is glycation, where sugars can react with proteins and other molecules, forming products that may stiffen tissues over time. This can affect blood vessels, skin, tendons, and other structures. When arteries become stiffer, the heart and circulation face different demands. When skin loses elasticity, wrinkles form. When joints and connective tissues change, movement may feel less smooth. These visible signs are not superficial in the sense of being meaningless. They are surface expressions of deeper material changes. The skin is not just looking older. Its collagen, elastin, hydration, cell turnover, immune environment, and sun exposure history have all been shaping its condition for years. Sunlight, especially ultraviolet radiation, can accelerate skin aging by damaging molecules and altering structural proteins, which is why sun exposure leaves such a strong signature on the body. Some aging comes from inside, but some is written by the environment. This is why lifestyle matters, but not in a simplistic blame-based way. Sleep, nutrition, movement, stress, social connection, pollution, infections, smoking, alcohol use, and medical care can influence the pace and pattern of aging. But genetics, early life conditions, economic circumstances, accidents, and random biological events also play roles. No one ages by willpower alone. The science should not become moral judgment. It should become understanding. Muscle aging gives a clear example of many processes working together. With age, people can lose muscle mass and strength, a process called sarcopenia. This is influenced by physical activity, hormones, nerve signals, inflammation, nutrition, mitochondrial function, and how well muscle stem cells repair tissue. Resistance training and adequate protein can help many people maintain or improve muscle function, but the body's response still depends on health, age, disease, and consistency. Bone aging, brain aging, immune aging, skin aging, and vascular aging all follow their own patterns, linked but not identical. Your immune system, for instance, may become less flexible with age, responding less strongly to some new threats, while also being more prone to chronic inflammation. This is one reason older adults can be more vulnerable to certain infections and may respond differently to vaccines, though vaccines remain extremely important because they help train immune protection. The brain also changes with age, but not in one simple direction. Some processing speed may decline, some kinds of memory may become less reliable, and the risk of neurodegenerative disease increases. But vocabulary, emotional regulation, pattern recognition, and knowledge can remain strong or even deepen in many people. Aging does not erase the mind in one uniform way. It changes the balance of abilities, and disease is not the same as normal aging. Dementia, for example, is more common with age, but it is not an inevitable part of growing older. That distinction matters. If we treat all decline as normal, we may ignore disease. If we treat all aging as disease, we may fear every change. The honest path is more careful. Aging increases vulnerability, but it is not one single illness. It is a shifting landscape of biological risk and adaptation. Scientists sometimes speak of hallmarks of aging, meaning broad categories of change that appear across organisms, such as genome instability, telomere shortening, epigenetic changes, loss of protein balance, altered nutrient sensing, mitochondrial dysfunction, cellular senescence, stem cell exhaustion, and changed communication between cells. These hallmarks are not separate boxes, they are connected. Damage can trigger senescence. Senescence can increase inflammation. Inflammation can affect tissue repair. Poor repair can increase dysfunction. Metabolic changes can influence stress responses. The body becomes a network of feedback loops. This is why anti-aging claims are often too simple. A cream cannot solve aging. A supplement cannot erase the entire network. A single food cannot reset biology. Some interventions are promising in research, and scientists study drugs, senolytics, caloric restriction pathways, exercise, sleep, nutrition, and regenerative medicine. But translating findings safely into longer, healthier human life is difficult. The real goal is not just lifespan, the number of years lived, but health span, the number of years lived with function, independence, and quality. A longer life without health is not the same as a better life. Aging research is trying to understand how bodies lose resilience, and how that loss might be slowed, delayed, or treated in specific ways. But even now, without fantasy, the science teaches something powerful. Aging is not a single destiny arriving all at once. It is a collection of processes, and different processes may be influenced differently. Movement can support muscle and metabolic health. Sleep can support repair and regulation. Nutrition can provide materials the body needs. Avoiding smoking and excessive ultraviolet exposure can reduce certain damage. Managing chronic disease can protect organs. Reality obeys rules that feel impossible when you notice them. Reality becomes stranger when you stop asking what exists and start asking what it is allowed to do. A stone falls, flame rises, water flows, metal bends, bodies heal, storms gather, clocks tick, seeds grow. And most of the time you move through these events without noticing the hidden permissions beneath them. The world feels natural because it is consistent. You drop a cup and expect it to fall. You touch ice and expect cold. You light a match and expect fire to spread, only if fuel and oxygen are present. Ordinary life is built on trust in rules so familiar that they disappear. But when you look closely, those rules begin to feel impossible. Not because they are false, but because they are so precise, so universal, and so deeply layered that the simple world you thought you lived in becomes a surface over something far more astonishing. Reality is not a loose collection of events. It is a system of constraints. Things happen not only because something pushes them, heats them, or breaks them, but because deeper laws decide what kinds of change are possible in the first place. Energy can transform, but it is not casually created from nothing in ordinary physical processes. Momentum can move from one object to another, but it must be accounted for. Heat tends to spread from hotter places toward colder ones because disorder has more ways to arrange itself than order. Chemical reactions do not occur simply because substances meet. They need the right conditions, the right energy, the right pathways. Living cells do not stay alive by ignoring physics. They survive by using physics with extraordinary precision, taking in energy, building order locally, and releasing waste into the larger world. This is one of the first deep lessons. Nature is not chaos wearing a mask. It is permission and limitation working together. Every event is a negotiation between what tries to happen and what the rules allow. A snowflake can grow into a complex shape because water molecules attach under certain temperatures and humidity conditions. Guided by molecular structure and environmental variation, a river curves because flowing water, sediment, gravity, resistance, and landscape interact over time. A soap bubble becomes round because surface tension pulls its film toward the smallest area for the volume it contains. A flock of birds can form shifting waves in the sky because each bird responds to neighbors, and simple local reactions create large-scale motion that looks choreographed. None of these things require a hidden artist drawing every detail. The rules are enough, but that is exactly what makes them feel so strange. The universe can produce beauty without intending beauty, order without a planner inside each pattern, complexity without every piece understanding the whole. This is called emergence, simple interactions creating behavior that seems richer than the parts alone. A single water molecule is not wet in the way your hand experiences wetness. A single neuron is not a thought. A single ant is not a colony. A single note is not a song. But when many parts interact under the right rules, new properties appear. The whole does things the pieces cannot do alone. That does not make the whole fake. It makes it emergent. Your mind, your body, weather, ecosystems, markets, languages, traffic, and galaxies all contain some version of this lesson. Large patterns can arise from small rules repeated across time, and sometimes those patterns become difficult to predict even when the rules are simple. This is where chaos enters, not as randomness, but as sensitivity. In some systems, tiny differences at the beginning can grow into huge differences later. Weather is the classic example. The atmosphere obeys physical laws, but its future depends on so many interacting variables that small uncertainties can expand until prediction becomes limited. This does not mean weather has no rules. It means the rules create complexity too rich for perfect long-term forecasting. Reality can be lawful without being easily predictable. That distinction matters because people often confuse mystery with lawlessness. If we cannot predict everything, we assume something must be missing or magical. But sometimes the opposite is true. The rules are there. They are just powerful enough to create outcomes. No simple mind can follow step by step. The same world that gives you reliable gravity also gives you turbulent clouds. The same physics that lets engineers build bridges also lets a river carve unpredictable channels. Order and uncertainty are not enemies. They are woven together. Another hidden rule is scale. What matters at one size may barely matter at another. Surface tension can dominate tiny droplets, while gravity dominates oceans. Air resistance can shape the fall of a feather, while a heavy stone seems to ignore it. Friction can be a nuisance in a machine, but without it you could not walk. Quantum effects rule the behavior of atoms, while larger objects usually appear stable because countless microscopic possibilities average into familiar patterns. The world changes its personality depending on how closely you look. This is why reality feels impossible when noticed. Your intuition is trained at human scale, but nature is not limited to human scale. You live in the middle, too large to feel atoms directly, too small to sense planetary motion through your body, too slow to notice many cosmic changes, too fast to see geological patience. Your senses evolved to help you survive in a narrow band of reality, not to reveal the full architecture of existence. So the world you experience is useful but incomplete. Science expands that window. It shows that stillness may hide motion, silence may hide vibration, darkness may hide radiation, emptiness may hide structure, and simplicity may hide entire networks of cause. Even the idea of a law of nature is strange when you sit with it. A law is not a police officer forcing matter to obey. It is a pattern so consistent that matter has never been seen to violate it under the conditions tested. The law is not written on a wall somewhere outside the universe. It is the universe behaving with deep regularity. Why should reality be regular at all? Why should the same rules work in a laboratory, inside a star, beneath the ocean, and across distant galaxies? Why should mathematics, a language invented and discovered by human minds, describe so much of what nature does? There are philosophical answers, scientific approaches, and open questions, but no simple emotional explanation fully removes the wonder. The consistency of reality is what makes knowledge possible. If the rules changed every morning, memory would fail, engineering would fail, science would fail, and life itself could not maintain its delicate processes. You exist because the universe is stable enough to be learned by cells long before it is understood by minds. Evolution depends on regularity. A body can adapt only if patterns persist. A brain can predict only if the world has habits. A civilization can build only if matter behaves tomorrow like it did yesterday. In this sense, every ordinary action is an act of trust in cosmic consistency. When you boil water, charge a phone, take medicine, plant seeds, or step onto a floor, you are relying on reality to keep its agreements. Yet those agreements can feel impossible because they do not care whether they seem intuitive. Fire burns because molecules react and release energy under the right conditions, not because flame has a desire to consume. Ice floats because solid water has a structure less dense than liquid water, a rare property that helps lakes freeze from the top and protects life below. The sky appears blue because shorter wavelengths of sunlight scatter more strongly in the atmosphere, not because blue is painted onto the air. A mirror reflects because its surface electrons respond to incoming light in a coordinated way. Your voice reaches another person because pressure waves travel through air, strike the ear, and become nerve signals. Each explanation removes one layer of mystery while revealing another layer beneath it. That is the rhythm of learning. The world becomes less magical in one sense and more astonishing in another. You stop needing false miracles because the real mechanisms are already enough. And perhaps this is the deepest point. Rules do not make reality boring. Rules make wonder possible. A universe with no rules would not be free. It would be incoherent. Nothing could form, last, grow, remember, or mean anything. Structure needs limits. Music needs intervals. Language needs grammar. Life needs boundaries. The same laws that prevent impossible things also allow possible things to become rich. Because energy behaves consistently, stars can shine. Because atoms bond in reliable ways, chemistry can build cells. Because cells follow biochemical rules, bodies can repair, sense, and adapt. Because nervous systems process signals with structure, experience can arise. Because cause and effect usually hold well enough at our scale, memory can become guidance. The limits are not only cages, they are the shapes that let existence become something instead of everything dissolving into nonsense. So when reality obeys rules that feel impossible, the impossibility is not in the rules themselves. It is in the gap between the small story your senses tell and the deeper story science reveals. You thought the world was made of objects, but it is also made of relationships. You thought events simply happened, but they unfold through constraints. You thought stability meant simplicity, but stability can hide complexity working perfectly. Hot water can sometimes freeze faster than cold water. A cup of hot water can sometimes beat cold water to ice, and the strangest part is that science still treats this simple kitchen question with caution. It sounds wrong the moment you hear it, because your intuition draws a straight line. Hot water must first cool down to become cold water, and only then can it freeze, so cold water should always have a head start. That reasoning feels so clean that it almost seems impossible to challenge. Yet under certain conditions, hot water has been observed to freeze faster than colder water. This effect is often called the Mpemba effect, named after Erasto Mpemba, a Tanzanian student who noticed that hot ice cream mix could sometimes freeze faster than a cooler mix and helped bring attention to the question in the 20th century, though similar observations had been discussed long before. But the key word is sometimes. Hot water does not always freeze faster. It is not a universal rule, not a magic shortcut, not a simple proof that heat behaves backward. If you take two identical cups, one hot and one cold, place them in a freezer and repeat the test, The result can depend on details so ordinary they are easy to ignore. The shape of the container, the amount of water, the freezer temperature, whether the freezer has frost, whether the water is covered, how evaporation happens, how air moves around the containers, what counts as frozen, how pure the water is, how much dissolved gas it contains, and whether one sample supercools before turning into ice. This is why the Mpemba effect is fascinating, not because it gives one simple answer, but because it exposes how many hidden variables live inside an event we thought we understood. Freezing is not just water gets cold and becomes ice. Freezing is a process involving heat leaving the water, molecules slowing down, ice crystals beginning to form, impurities influencing crystal growth, surfaces helping or preventing nucleation, and the surrounding environment removing energy at different rates. One reason hot water may sometimes freeze faster is evaporation. Hot water can lose more mass as vapor before it freezes. If a cup of hot water evaporates enough, there is simply less water left to freeze, and a smaller amount can freeze sooner. Evaporation also carries away heat, because the molecules that escape tend to take energy with them. But evaporation alone does not explain every case, especially if the containers are covered or mass loss is too small. Another possible factor is convection, the internal circulation of water as warmer and cooler regions move. Hot water can create stronger circulation patterns while it cools, helping distribute temperature more evenly or bring warmer water to the surface where heat can leave faster. Cold water, depending on conditions, may not circulate in the same way. A third factor is frost and contact. In some freezers, a hot container can slightly melt frost beneath it, improving contact with the freezer shelf. Better contact can allow heat to flow away more efficiently once the melted layer refreezes, while a colder container may sit on insulating frost. That sounds like a tiny detail, but tiny details matter when the whole question depends on heat transfer. Dissolved gases may also play a role. Heating water can drive out some dissolved air, and this can change properties such as freezing behavior. Though this explanation is not always enough by itself. Then there is supercooling, one of the most important and surprising parts of the story. Water does not always freeze exactly at its usual freezing temperature. Very clean water in a smooth container can cool below that point and remain liquid if ice crystals do not get a good place to start. It may sit there, colder than expected, waiting for a disturbance or nucleation site before suddenly freezing. If cold water supercools more deeply than hot water in a particular setup, then the hot sample might begin forming ice sooner, even after starting warmer. This does not mean the hot water avoided cooling. It means the colder sample may have delayed the actual transition into ice. The race is not only to reach a temperature, it is also to begin freezing. That distinction matters. Ice formation is not merely about coldness. It is about structure beginning at the molecular level. Water molecules must arrange into a crystal lattice, and that first stable seed of ice can be surprisingly difficult to start under some conditions. This is why you can sometimes see supercooled water suddenly freeze when shaken or poured. It was already cold enough, but it had not yet organized into ice. The Mpemba effect lives inside this messy boundary between temperature, heat loss, phase change, evaporation, circulation, and nucleation. And because all of these factors can vary, scientists do not treat the effect as one single mechanism with one final explanation. Different experiments may produce different outcomes for different reasons. Some researchers even debate how to define the effect properly. Does freeze faster mean the first appearance of ice? Does it mean the whole sample becomes solid? Does it mean reaching a specific temperature? If two experiments use different definitions, they may seem to disagree even when both are honestly measured. This is what makes the subject more educational than a simple viral fact. It teaches that nature does not always answer vague questions cleanly. If the question is not precise, the answer can shift. Which freezes faster, hot or cold water? Sounds simple, but science must ask, how hot, how cold, how much water, what container, what environment, what purity, what surface, what airflow, what measurement, what definition of frozen? The real world is not a cartoon of one variable changing while everything else stays still. It is a network of conditions, and sometimes changing the starting temperature changes several other things at once. Hot water may evaporate more, circulate differently, lose dissolved gases, interact differently with its container, melt frost, or avoid certain kinds of supercooling. Cold water may keep more mass, cool differently, or delay ice formation.